Hello there and welcome to Life Beyond Seen, where quiet questions are given time and difficult science is allowed to arrive gently. Tonight, we are heading to one of the coldest and most remote places on Earth, not to the bright white surface that shows up in documentaries and weather maps, but far below it, under layers of ancient Antarctic ice, where liquid water has been hiding in the dark for a very long time. That idea sounds almost unfair at first, doesn't it? You look at Antarctica and think, surely this is the last place on Earth to have lakes. Snow, yes. Ice, certainly. Wind that could talk you out of your life choices, probably. But lakes. Real bodies of water beneath all that frozen weight. It feels like the sort of thing the planet should have mentioned more clearly. And yet, beneath that ice sheet, there are not just one or two strange pockets of water, but hundreds of subglacial lakes, discovered through radar, seismic work, satellite observations, and changes in the ice surface that hint at water moving below. The ice above them can be tremendously thick, but pressure, geothermal heat from below, and friction within the moving ice help keep some of that water from freezing solid. Now that alone would be enough to make a person sit up a little straighter in bed and think, hold on, there are hidden lakes under Antarctica, and we are only casually mentioning this. But the deeper question is even more interesting. If these lakes are there, if science knows they exist, if human beings have already sent machines to the moon, probes to Mars and cameras into the deep ocean, then why can't we just go and explore them properly? Why can't we lower a robust little robot into the water, switch on a light, and have it swim around like an obedient mechanical duck? Why can't we map the shoreline, sample the mud, check for life, and come back with neat little answers for the rest of us? The gentle but frustrating truth is that we can reach some of these places in limited ways, and we have sampled a few, but that is not the same thing as truly exploring them. To truly explore a hidden lake, you would want freedom of movement, repeated visits, clean measurements, trustworthy images, maybe long-term instruments, perhaps even a vehicle that could travel through the water and return with samples from more than one spot. You would want context. You would want to know whether what you found was typical or just local. You would want to be sure that the first thing to arrive in that ancient environment was not your own hose, your own drill water, your own microbes hitching a ride in on a cable like extremely uninvited tourists. And that last problem, the contamination problem, turns out to be one of the biggest reasons this story is so difficult. Before we go further, I'd love to know where you're listening from tonight. What time is it in your corner of the world right now? Are you hearing this in the late evening with rain outside, in the early hours when the house has finally gone quiet, or at some determinedly responsible afternoon moment where you're absolutely not meant to be drifting off? There is something fitting about that question tonight, because this whole story depends on distance and perspective. Somewhere you're listening from a room, or a train, or a sofa, or a bed. Somewhere far away, Antarctica is sitting under its own weather, keeping its own silence. And under that silence, hidden from the sky, are lakes no human being can simply walk up to and inspect. If you find this soothing, or interesting, or just a comfortable place to let your thoughts slow down for a while, do leave a like and subscribe to the channel. It helps this calm little corner reach more people who want science without the shouting. And for tonight's question, I think it helps to start with a very ordinary image. Imagine you found out there was an untouched room sealed inside a mountain. No door, no window, no power, no hallway, no record of who had been there before, because perhaps nobody ever had. You're told there may be living things inside. There may also be fragile clues about what the mountain and the climate were doing long before humans were around to name them. You're allowed one narrow opening to get in. Everything you lower through that opening might change the room forever. Suddenly this is not just a matter of access. It is a matter of how to arrive without wrecking the answer. That is very close to the problem scientists face with subglacial lakes. Some of these lakes may have been isolated from direct contact with the surface for very long periods of time. Lake Vostok, the largest known subglacial lake in Antarctica, lies beneath roughly 4,000 meters of ice, and estimates have suggested isolation on the order of hundreds of thousands of years. That kind of setting does things to the imagination. It makes people wonder about microbial life, unusual chemistry, preserved climate records, and the limits of survival. It also makes people nervous in exactly the right way, because the more unique an environment may be, the less casual you can afford to be when you enter it. You do not want to barge into a place like that with the scientific equivalent of muddy boots. And so the challenge begins long before anyone drills a hole. It begins with location, transport, weather, fuel, sterilization, engineering, permissions, and a level of planning that makes ordinary travel look delightfully reckless. Antarctica is remote even by Antarctic standards when you're talking about interior drilling sites. Equipment has to survive shipping, freezing, vibration, and delay. People have to live and work in dangerous cold. Systems that behave nicely in a laboratory may become temperamental once they are asked to operate on an ice sheet with relentless wind, limited time, and no convenient hardware store 2 streets over. Even reaching the lake is not like digging a backyard pond, unless your backyard is made of a kilometre or more of ice, and actively punishes optimism. Then there is the matter of the hole itself. In common imagination, drilling sounds straightforward. You make a borehole, lower instruments, and begin. But for subglacial lakes, a borehole is not just a passage. It is an event. The drill must cut through immense thicknesses of ice without introducing unacceptable contamination. The opening must stay usable in an environment that wants very badly to freeze it shut again. The water used in hot water drilling, where that method is chosen, has to be treated and cleaned. Instruments, hoses and cables have to be disinfected. In the Willans and Mercer Lake projects, teams use combinations of filtration, ultraviolet treatment, hydrogen peroxide, and carefully manage clean access procedures precisely because contamination was such a serious concern. That care is impressive, but it also reveals the central problem. The more responsibly you approach these lakes, the slower, harder, and more limited the exploration becomes. There is an almost cruel irony in that the very reason these lakes are scientifically precious is also the reason scientists must behave with such restraint around them. If you want a dramatic expedition with broad freedom to improvise, this is not the place. What you need instead is discipline, clean entry, controlled sampling, constant awareness that a tiny mistake made at the top of the ice can become a scientific headache at the bottom. A lake that has been sealed away for ages does not give you many chances to shrug and say, "Never mind, we'll tidy that up later." Even methods that seem practical on paper can become troublesome when cleanliness and reliability are considered together. The British Antarctic Survey's environmental evaluation for the proposed Lake Ellsworth exploration spelled this out very clearly. It warned about contamination risks from substances in boreholes and from lowering equipment through them, and it noted that some alternative ideas, including thermoprobes, were not considered feasible in that context. That is a useful reminder that difficulty here is not only about bravery or funding, it is about the physics of ice, the chemistry of water, the biology of contamination, and the uncomfortable fact that every solution creates a new problem waiting politely beside it. A person might reasonably ask, but surely if we can sample a lake, we can explore it. Not quite. Sampling is a glimpse. Exploration is a sustained relationship with a place. When scientists reached subglacial Lake Willans and later subglacial Lake Mercer using environmentally cleaner hot water drilling, that was a remarkable achievement. It gave researchers access to water, sediments, and evidence of active microbial ecosystems. But a narrow borehole through thick ice does not turn a buried lake into an open research station. It gives you a controlled window, a very precious one, through which you can lower selected instruments for limited tasks. Imagine trying to understand an entire cave system through a letterbox without touching the frame, scratching the paint, or dropping crumbs inside. You might learn something real and important. You would still not call it full exploration. That difference matters because the phrase truly explore carries a lot more than simple access. It means moving through an environment on its own terms. It means seeing variation from one place to another. It means following channels, identifying boundaries, understanding how water flows in and out, and learning whether the lake is stable, shallow, deep, muddy, oxygen poor, chemically strange, or connected to a larger hidden drainage network. It means being able to return, compare, verify, and say, with confidence that the life or chemistry you detected was not just from one convenient location under one convenient hole. Antarctica's subglacial hydrology appears to be dynamic in many places, with water moving between lakes and through under-ice systems, which makes these environments even more interesting and even less easy to summarize from a single narrow access point. There is also a psychological trap here, and science communication falls into it all the time. We hear that a place has been reached, and our minds quietly replace the word reached with understood. They are not the same. We hear that a probe went down, so we picture a tidy digital map, cheerful footage, and a narrator saying, "Here is the lake floor and here are the local residents going about their microbial business." But often the reality is more modest and more careful, because careful is what the setting demands. A few instruments, a narrow opening, a tight schedule, limited visibility, limited mobility, limited certainty, plenty of insight, yes, full freedom, no. And if that sounds slightly frustrating, it should. That frustration is part of what makes this subject so compelling. Human beings are used to solving access problems by scaling up. Bigger vehicle, better camera, longer cable, more power, another mission. In many environments that works reasonably well, under Antarctic ice, scale alone does not save you. A larger machine is harder to sterilize, harder to lower, harder to retrieve, and more capable of getting stuck in a place where maintenance visit is not a comforting phrase. One modern paper on subglacial operations even discusses the risk of autonomous sondes freezing into ice if heating fails, along with concepts for rescue drilling. That is not the sort of sentence that fills an engineer with peaceful ease. It is, however, very revealing. Even our tools need rescue plans down there. So tonight, as we begin this journey, it helps to hold two ideas at once. First, subglacial lakes are real, scientifically rich, and already important enough that researchers have developed remarkably careful methods to detect, access, and sample some of them. Second, detection is not exploration, access is not freedom, and a single clean borehole is not the same as entering a landscape in any deep or complete sense. We can approach, we can infer, we can sample, we can learn. Yet there remains a stubborn boundary between touching a hidden lake and truly exploring it. That boundary is made of distance, cold, pressure, contamination risk, engineering limits, time, cost, and simple humility. It is also made of respect, because every time science gets close to one of these sealed waters, it has to ask a difficult question. Not only can we reach this place, but how should we? How much presence is too much presence? When does curiosity become disturbance? And if there is life there, however small, however strange, do we learn more by pushing deeper, or by proceeding so carefully that progress feels almost slow to the point of teasing? That is where this story becomes more than a tale of hidden water under ice. It becomes a story about the limits of exploration itself, not the dramatic movie trailer version where humans conquer the unknown in one inspiring montage, but the quieter and more honest version, where the unknown pushes back by being delicate, inaccessible, and easy to ruin. Antarctica does not forbid us from trying. It simply insists that trying comes with conditions. And once you see those conditions clearly, the hidden lakes stop looking like secret rooms waiting to be opened, and start looking more like places we are only just learning how to approach without changing them. Which brings us to the next step in this story. Because before we can understand why true exploration keeps slipping out of reach, we need to spend a little time with the lakes themselves, where they are, how scientists know they are there, and why so much of this begins not with diving into dark water, but with listening very carefully to ice. When most people picture Antarctica, they picture the top of it. They imagine a white surface, a flat horizon, maybe some rough weather, maybe a scientist in a heavy coat trying not to lose feeling in their face. What they usually do not picture is a hidden landscape underneath all that ice, with water collected in hollows, channels running between basins, and entire lakes sealed beneath the ice sheet. That is the first thing worth slowing down for here, because it changes the shape of the whole story. Antarctica is not just ice all the way down. In many places there is a bed of rock below, and between the ice and that bed there can be water. Sometimes that water spreads thinly, sometimes it moves through drainage systems, sometimes it gathers in one place long enough, and in enough volume, for scientists to call it a subglacial lake. These lakes are not a rumour, and they are not a single dramatic exception. Researchers have confirmed hundreds of Antarctic subglacial lakes through radar sounding and satellite measurements, and newer satellite work in 2025 pushed the number of known active lakes alone to 231. That can sound strange at first because cold seems simple in the imagination. We tend to assume that if a place is freezing at the surface, then anything beneath it must be even more frozen. But the underside of a massive ice sheet does not behave like the top shelf of a neglected freezer. Ice is heavy, and when you pile up hundreds or thousands of meters of it, the pressure at the base rises enormously. Add heat coming up from the earth below, plus friction from ice moving across the bed, and some of that basal ice can melt. Then the thick ice overhead acts as insulation, keeping that water from simply flashing back into solid ice the moment it forms. Researchers describing the global inventory of subglacial lakes have noted that these lakes can form from geothermal heating from below, from water reaching the bed, and from the way overlying ice insulates the water from the colder air above. So the picture is not ice, then more ice. It is better to think of a very thick lid with a surprising number of wet places underneath it. It also helps to let go of the idea that these lakes are all one kind of lake. That is another place where the mind quietly simplifies things. We hear subglacial lake and think of one hidden oval of water. Very still, very mysterious, probably waiting in perfect silence for a camera. In reality, some are large and long-lived, some are smaller and more active, some fill and drain over time, and some appear to be part of wider drainage systems that move water from one place to another. The 2022 Global Inventory, led by researchers at Sheffield, catalogued 773 subglacial lakes worldwide, and noted that around 80% were considered stable, while roughly 20% were active, meaning they gain or lose water over time. In Antarctica, satellite records have shown lakes filling, draining, and connecting in ways that reveal a much more dynamic plumbing system than people once imagined. So when we say the lakes hidden under Antarctica, we're not talking about one lonely body of water under a spotlight. We're talking about a whole class of hidden environments, with different sizes, behaviours, and degrees of connection. That difference between stable and active matters more than it first appears. A stable lake is easier for the imagination to handle. You picture a place sitting there, undisturbed, as if it were tucked away in storage. An active lake is less polite. It reminds you that Antarctica is not simply storing frozen things, it is running systems. Water can move beneath the ice sheet, and when it does, the ice above can rise or sink by measurable amounts. Scientists have used those surface changes to detect what is happening below. That is one of the most satisfying parts of this field, because it sounds almost impossible until someone explains it slowly. If a lake under the ice fills with more water, the ice above may lift slightly. If it drains, the surface can settle. Satellites are able to measure those changes in elevation with enough precision to reveal a hidden hydrological world. Earlier IceSat work identified 124 active lakes between 2003 and 2008, and more recent cryosat analysis detected 85 additional active lakes and mapped 5 interconnected subglacial lake networks. It is a remarkable way of seeing something that nobody can simply walk down and inspect. There is a nice humility in that method too. Science did not find these lakes by kicking open a door and shining a torch around. It found many of them by being patient with indirect clues. Radio echo sounding has been one of the key tools here. Radar waves are sent down through the ice, and the reflections help researchers figure out where the bed is, how smooth it is, and whether there is liquid water below. Water and rock reflect differently. A flat, bright radar reflector beneath the ice can be a very strong hint that a lake is there. That kind of radar work has been building the Antarctic picture for decades, while satellite altimetry added a second way of detecting the more active lakes. So the map of hidden Antarctica has been drawn through instruments, inference, repeat measurements, and a great deal of stubbornness. That history matters because it explains why these lakes entered science gradually. Their existence was identified in the 1960s, but only later did researchers begin to realize just how many there were and how varied they might be. Lake Vostok is usually the example that gets everyone's attention first, and that is understandable. It is the largest known subglacial lake in Antarctica, buried under roughly 4 kilometers of East Antarctic ice. By the mid-1990s, scientists recognized it as not merely a damp patch under ice, but a very substantial body of water, and NASA's astrobiology materials describe it as around 500 meters deep. Older and newer summaries alike keep returning to it because it is so large and so suggestive. A lake that size under that much ice forces the imagination to behave differently. You stop thinking in terms of puddles and start thinking in terms of geography. The old joke would be that Antarctica was already doing hidden basements before it became fashionable. But even Vostok is only one part of the story. The danger with famous examples is that they make the rest sound like supporting actors, when in reality Antarctica contains a far broader set of hidden water bodies than one famous lake can represent. And some of the most scientifically useful lakes are not the largest ones. Lake Willans, for instance, became famous not because it dwarfs everything else, but because scientists managed to reach it cleanly enough to sample it. It lies beneath about 800 meters of West Antarctic ice, and work there provided the first direct access to a subglacial Antarctic lake, without the kind of contamination that would have made the results much harder to trust. What turned up was not an empty, sterile chamber, but a living microbial ecosystem in deep, dark water. NASA summaries of the Wizard project describe living cells in the samples, and later work reported thousands of microbial species, including organisms tied to chemical energy sources rather than sunlight. That is one reason these lakes matter so much. They are not interesting only because they are hard to reach. They are interesting because they may contain active biology, unusual chemistry, and records of how life and water behave under conditions that most of the planet never experiences. Mercer Subglacial Lake offers a slightly different lesson. It lies around 1,200 meters beneath the West Antarctic ice sheet, and is part of a hydrologically active region tied into the Willans ice plain system. The SALSA project description makes clear that Mercer receives water from both East and West Antarctica, is influenced by upstream drain and fill cycles, and sits within a connected network that scientists wanted to understand in spatial context, rather than as a single isolated basin. That is useful because it pushes against the old image of lakes hidden like marbles in separate drawers. Some of them are better understood as nodes in a subglacial water system. Water can move through these environments, and that movement affects the ice above. British Antarctic survey summaries have stressed that movement of water from one lake to another can alter glacier flow, which means these hidden lakes matter not only to microbiologists and geochemists, but also to people trying to understand ice sheet behaviour and future sea level change. That wider context is one of the reasons Antarctica's hidden lakes are so easy to misunderstand from a distance. They sound like oddities, like trivia for very committed people in oversized gloves. In fact, they sit in the middle of some of the biggest practical questions in polar science. How fast does ice move? How does basal water lubricate that motion? Which parts of an ice sheet are stable, and which are more responsive than they look from above? Water at the bed can reduce friction, alter stress, and change how quickly ice streams transfer ice toward the ocean. Researchers do not bring up subglacial lakes merely because they enjoy startling everyone at dinner with facts about water under Antarctica. They bring them up because hidden water changes the mechanics of the whole ice system. Even when the lakes themselves are difficult to observe directly, their existence matters to glaciology in a very practical sense. In that way, these lakes are not just hidden features, they're working parts of the continent. There is another correction worth making here, because the phrase hidden lakes can accidentally make them sound neat and well-bounded, like blue shapes on a school atlas. Some are well-defined enough for that kind of mental picture. Others are shallower, more changeable, or best understood through repeated observations rather than a single perfect outline. A lake may be active over months or years. Its footprint can vary during fill and drain cycles. Surface elevation changes do not hand scientists a tidy scenic overhead shot with labels and a little gift shop in the corner. They provide evidence that has to be interpreted. Even radar, for all its power, gives a scientific picture rather than a holiday brochure. That may seem obvious, but it matters for the tone of this whole subject. We know these places exist, but we often know them first as signals, reflections, deformations, and measurements. The map arrives before the view. The numbers arrive before the experience. It is a strangely modern way to meet a landscape. That is partly why people sometimes feel a little cheated when they first learn about subglacial lakes. They expect the discovery moment to come with a dramatic reveal, and instead it often comes with geophysical evidence. No choir, no sweeping music, just a group of scientists pointing out that the ice surface rose here, fell there, and the radar return is unusually bright in this region, which collectively means there is a lake where nobody can see one. But there is something satisfying about that restraint. It is closer to the real work of science. Antarctica does not often hand over its hidden structures in a theatrical way. It lets you notice them by degrees, and only if your instruments are good and your patience is better. That is how the continent has accumulated this quiet second geography beneath the first one. On top, the visible ice sheet. Below, a more complicated world of water storage, drainage, sediments, chemistry, and in at least some cases, life. And then there is the simple emotional fact of it. A lake under ice hits the imagination differently from a buried rock layer or a hidden fault. Water feels immediate, familiar. You and I know what a lake is. We know what it means to stand at the edge of one. We know about shorelines, stillness, mud, reflections, the general suspicion that your shoes are not going to enjoy what happens next. So when you hear that there are lakes under Antarctica, your mind rushes to make them familiar. It tries to put an ordinary lakeside scene underground. But these are not ordinary lakes with the lights turned off. They exist in darkness, under immense pressure, beneath ice that may be hundreds to thousands of meters thick. And in some cases they may have been separated from the direct surface world for extremely long periods. Even when they are active and connected to moving water systems, they remain unlike the lakes most of us have known. The name is familiar. The environment is not. This is where the topic becomes more than a list of strange facts. Once you understand that Antarctica holds not one secret lake but many, and that those lakes can be stable, active, shallow, deep, isolated, or networked, the entire continent starts to look different. Its frozen surface stops being the whole story. The visible Antarctica becomes a roof. The radar lines, satellite records, and drilling projects become ways of listening for what is underneath. And that turns a blank white mass into a place with layers, not just of ice and time, but of environments. Some are ancient, some are changing right now. Some influence ice flow in ways that matter to the rest of the planet. Some may contain organisms that survive without sunlight drawing energy from chemistry instead. All of that sits below the surface people usually picture when they say the word Antarctica. The hidden lakes are not side notes. They are part of the structure of the place. And once that hidden structure is in view, another thought arrives almost automatically. If these lakes are down there, how long have they been there? Not simply as patches of water, but as environments with their own histories. How long has a particular basin held water? How long has a microbial community, if one exists there, gone about its business without daylight? How long has a lake remained separated from the weather, from birds, from dust, from the ordinary traffic of the surface world? Scientists have said that some Antarctic subglacial lakes may have been sealed off for millions of years. That possibility changes the feeling of the whole subject. We are no longer just discussing hidden geography. We are discussing places with long uninterrupted histories, and histories that may be unlike almost anything on the accessible surface of Earth. Once you begin thinking in those terms, the lakes stop being surprising features under ice, and start becoming sealed environments with their own timelines, which is where the next part of this story begins. Once that idea settles in, the hidden lakes under Antarctica start to feel less like an odd feature on a geophysical map, and more like places with biographies. Not biographies in the human sense, thankfully, because a lake with a social calendar would be difficult enough on the surface and completely unreasonable under 4 kilometres of ice. But histories certainly, durations, conditions that have lasted long enough to shape chemistry, sediment, circulation, and perhaps life itself. That is where the subject shifts from surprising to genuinely unsettling in the best possible way. We're not simply looking at water hidden from view. We're looking at environments that, in some cases, may have been cut off from the atmosphere and from each other for immensely long periods of time. British Antarctic Survey notes that many Antarctic subglacial lakes have been isolated from each other and from the atmosphere for millions of years, and NASA's astrobiology reporting makes a similar point, describing some subglacial lakes as sealed off from the outside world for millions of years. That phrase, sealed away for millions of years, has a dramatic ring to it, and it deserves to be handled carefully because it is both true in an important sense and easy to oversimplify. It does not always mean that every single drop of water in a given lake has sat perfectly still and untouched for an uninterrupted span of millions of years. In some systems, water can circulate, freeze onto the base of the ice sheet, or be replaced over time. Lake Vostok is a good example of why this distinction matters. NASA notes that Lake Vostok may have been isolated from the atmosphere for millions of years, while some studies estimate isolation from direct surface inputs at around 420,000 years. At the same time, research summarised by Columbia and PubMed found that Lake Vostok's water residence time may be about 13,300 years, meaning the water itself can turn over even while the environment as a whole remains physically buried and cut off from ordinary atmospheric contact. So when scientists speak about a world sealed away, they often mean a buried system whose conditions have remained isolated on geological timescales, not a jar of water screwed shut and never disturbed. And that distinction is more than a technical footnote. It changes how we think about age. There is the age of the chamber, the age of the connection to the atmosphere, the age of the sediments, the age of the ice cover, and the residence time of the water currently present. Those are related, but they are not identical. People sometimes hear that a lake is millions of years old and imagine the exact same pool, held motionless like a forgotten glass on a windowsill. Antarctica is subtler than that. A lake can be ancient as an environment while also being dynamic in the way water enters, leaves, freezes and melts within the system. A closed lake may preserve separation from the surface for extraordinary lengths of time, while an active or connected lake may exchange water on much shorter timescales. NASA's astrobiology overview separates subglacial lakes into more isolated closed systems and those connected to broader subglacial hydrological networks, and that is an important distinction for everything that follows, from biology to chemistry to how much the phrase "sealed away" really applies. Still, Even with that caution in place, the ages involved are astonishing. The reason these lakes attract so much interest is not just that they are hidden, but that they may have persisted beneath ice over intervals that dwarf normal human experience. BAS has emphasised that many Antarctic subglacial lakes may have been isolated for millions of years, while an earlier BAS summary on Antarctica's hidden lakes described East Antarctic subglacial conditions in terms of about 1 million years, and Lake Ellsworth as isolated from the surface for hundreds of thousands of years. NASA's astrobiology work likewise points to lakes that may have been shielded from the surface or atmosphere for thousands, tens of thousands, and perhaps millions of years depending on the system. Even the lower end of those ranges is enough to produce an environment unlike anything most of Earth's surface offers. The higher end pushes the story into geological time, where continents shift, climates swing, and entire species appear and vanish, while a lake remains buried in darkness. That sort of timescale is hard to feel properly, so the mind reaches for comparison. Human recorded history covers only a few thousand years. Agriculture, cities, empires, and writing all fit inside a period that would look brief beside the possible isolation history of some Antarctic subglacial environments. Even the better-known ice core records, remarkable as they are, stretch back hundreds of thousands of years rather than tens of millions. The point is not to turn every sentence into a dramatic whisper about deep time, because that gets tiring quite quickly. The point is that subglacial lakes sit in a category where normal intuition stops being useful. A place that has been physically protected from the atmosphere for such long spans does not just preserve water, it preserves conditions, it preserves chemical limits, it preserves a style of existence that has not needed daylight, seasons in the ordinary sense, or fresh organic inputs from the living surface world. That is what makes these lakes feel less like hidden ponds, and more like separate rooms in Earth's long memory. The absence of sunlight is one of the first things to appreciate properly. It sounds obvious, but it is not trivial. On the surface, sunlight drives most familiar ecosystems either directly or indirectly. Plants use it, algae use it. Food webs are built around organisms that depend on it, or on other organisms that do. A subglacial lake has no such convenience. BAS notes that microbes in these settings cannot rely on photosynthesis, and instead must obtain energy by processing chemicals, especially those concentrated in sediments on the lake bed. NASA makes a similar point when discussing subglacial environments as analogues for icy worlds, emphasizing that life in such lakes would have to persist under extreme cold, low nutrient availability, and no sunlight at all. That means the age of a sealed lake is not simply a clock. It is a long test of whether a biological system can survive on chemistry alone, and for how long. Then there is the matter of mixing, which sounds like a dull technical concern until you realise how much of a world depends on it. Surface lakes are stirred by wind, sunlight, seasonal heating, and contact with the open air. None of that applies here. BAS points out that in ordinary lakes, wind and solar heating help drive circulation, whereas subglacial lakes lack those familiar forces. A lake under ice may therefore separate into different layers with very different conditions, or it may circulate through other mechanisms such as melting, freezing, pressure-driven flow, or the shape of the basin itself. That means a subglacial lake can become chemically stratified, with some zones more oxygen-rich, some saltier, some better supplied with nutrients than others. In other words, a buried lake may not be one simple habitat. It may be several stacked habitats sharing the same dark address. And if a lake has been like that for a very long time, the importance of each layer becomes much greater. It is tempting here to picture a quiet, still body of water, almost decorative in its own eerie way, but that is often the wrong mental image. Even a long isolated environment can be active internally. Lake Vostok, for example, is not just a sealed chamber of undisturbed water. Studies summarised by Columbia and PubMed indicate that water can melt in, freeze onto the underside of the ice sheet, and effectively cycle through the system over thousands of years. BAS's 2021 work on the prospects for life in Antarctic lakes also highlights the importance of circulation because mixing can distribute nutrients, oxygen, and sediment through the water column, affecting where life may be most detectable. So a world can be isolated without being dead, and ancient without being static. That is one of the reasons these lakes are so interesting and so difficult. Their age is not the age of a fossilized snapshot. It is the age of a living set of constraints. Sediments at the bottom of these lakes add another layer to the story, and perhaps the calmest way to put it is that mud becomes very important once you stop underestimating time. Sediments accumulate what the water above has done, what minerals have entered the lake, how chemical conditions have shifted, and sometimes whether biological material has been present. The Antarctic subglacial lake literature has long treated lake sediments as potentially valuable records of past environmental change, and the 2016 assessment of Antarctic subglacial lake coverage noted that because some of these lakes may be millions of years old, sediment layers tens or even hundreds of meters thick could have accumulated, preserving climate and biological information that stretches far beyond what current ice cores alone can deliver. The US National Science Foundation made much the same point about Lake Vostok years earlier, noting that sediment samples from its floor could extend climate records into spans of millions of years. That is one reason people become a little reverent around these environments. A borehole into a lake is not just an opening into water, it may be an opening above a long, undisturbed archive. And once you understand that, the old phrase sealed away stops sounding like an overexcited slogan and starts sounding almost insufficient. A sealed room is one thing, a sealed record is another. Imagine the difference between entering an old building and opening a cabinet that has not been disturbed since before your language existed. The age changes your behaviour. It makes you slower. It makes you less casual. It makes you aware that some of the value lies not merely in what is there, but in the fact that it remained there undisturbed. Antarctic subglacial lakes bring exactly that kind of caution into science. They are interesting because of what they may contain, but also because their isolation itself is part of the evidence. The longer a system has remained separated from the atmosphere or surface inputs, the greater the chance that it records conditions not easily found elsewhere. There is also the biological question, which tends to arrive quietly and then refuse to leave. If a lake has been isolated for immense periods, what survives there, if anything, and how would it change over time? BAS has said that any life in such lakes could be equally ancient in its regional isolation, offering clues about how organisms adapt under persistent extreme cold. NASA's reporting on Lake Willans showed that at least some Antarctic subglacial lakes do support microbial ecosystems, including methanotrophs and other organisms making use of chemical energy rather than sunlight. That does not mean every buried Antarctic lake hosts an active or diverse ecosystem, and scientists are careful about that point. But it does mean the question is no longer a science fiction flourish. The possibility of life in isolated subglacial lakes is a serious research issue, grounded in real discoveries from cleaner drilling campaigns and in models of how chemistry can sustain microbes beneath ice. At the same time, age does not automatically mean biological richness, and isolation does not automatically mean evolutionary wonder, in the dramatic sense people enjoy imagining. A lake can be ancient and still be starved, quiet, chemically difficult, and sparsely inhabited. BAS's 2021 study focused in part on where microbes might be most likely to exist and how lake circulation affects whether nutrients and oxygen can be distributed well enough for life to be easier to detect. That is a useful corrective. A long isolated environment could produce distinctive adaptations, but it could also be patchy, harsh, and frustratingly poor in the signs we most want to find. Millions of years in darkness do not guarantee an abundant hidden biosphere. They guarantee only that any surviving life must have learned to tolerate a very strict landlord. Lake Vostok often returns here because it captures this mixture of promise and caution better than almost any other example. NASA's astrobiology overview describes it as the largest known subglacial lake on Earth, covered by around 4,000 meters of ice, with some studies estimating isolation from direct surface inputs at about 420,000 years, while also noting the broader view that it has been isolated from the atmosphere for millions of years. The important thing is not to force those numbers into false contradiction. They refer to different aspects of isolation and different ways of describing the system. What matters for the story is that Vostok represents an environment buried so deeply and for so long that even limited access to it raises extraordinary scientific hopes and equally serious contamination concerns. Its age is not a decorative feature attached to a famous lake. It is the reason the lake matters. The same is true, on a smaller scale, for other lakes that are not as famous but are arguably just as revealing. BAS's older summary of Lake Ellsworth described it as isolated from the surface for hundreds of thousands of years, beneath about 3.2 kilometres of West Antarctic ice. That is shorter than the largest claims made for parts of the East Antarctic system, but it is still a span long enough to create an environment the surface world has not casually interrupted. NASA's distinction between more closed systems and more connected lakes helps here again. Not every subglacial lake is sealed to the same degree, and not every lake tells the same story. Some are better thought of as ancient enclosed habitats. Others are more like buried stations along a moving water route. The age and degree of isolation change the scientific meaning of each one. This is also where the comparison to icy moons becomes more than a publicity habit. NASA and BOAS both point out that Antarctic subglacial lakes can serve as analogues for environments on Europa, Enceladus, and other icy worlds, because they combine cold, darkness, pressure, and limited chemical energy in ways that surface ecosystems do not. The comparison is useful not because Antarctica is a perfect stand-in for another world, but because it gives researchers a real place to test how life might survive when sunlight is absent and access is difficult. A lake that has been separated from the atmosphere for immense spans under thick ice is about as close as Earth conveniently gets to practicing for extraterrestrial caution. And that word conveniently is doing unfair amounts of labour, because Antarctica is not convenient at all, but it is still better than Jupiter for field logistics. There is something else age does to a place, and it is less scientific but no less important. It changes the emotional tone of entry. If a lake has been physically protected beneath ice for thousands, hundreds of thousands, or millions of years, then drilling into it is not simply a clever technical feat. It becomes an intrusion into continuity. That is not a moral objection by itself, but it is a real weight. A sealed environment with a long independent history feels different from an ordinary difficult field site. A mistake there is not only a failed measurement, it may be the first human-caused disturbance in a system that has had no reason to expect us. This is why access protocols, contamination controls, and international scrutiny matter so much. The age of these lakes increases both their value and their vulnerability, and because those lakes are old in different ways, scientists have to think with unusual care about what exactly they hope to preserve. Is the priority the water chemistry, the sediments, the possibility of living cells, the structure of the water column, the clean distinction between different layers? In a younger, more connected lake, the concern may focus on accurate sampling of an active hydrological system. In a more isolated lake, the concern may broaden into preserving an environment whose scientific meaning lies precisely in how long it has remained apart. BAS's work on potential life in isolated lakes emphasises that whether and where life is detectable depends on circulation and sediment interactions. That means age alone is not enough. A million-year-old lake is not automatically easy to interpret. It may simply be ancient and complicated, which is in some ways the most Antarctic combination possible. By this point, the phrase, "a world sealed away for millions of years," should sound less like a dramatic label and more like a practical warning. It tells you that time is part of the science here. It tells you that isolation has consequences. It tells you that what lies beneath the ice may not just be hidden from view, but shaped by a long separation from the systems that usually define life at the surface. It also tells you why scientists cannot treat these lakes like routine drilling targets. The older and more isolated the environment, the more every later decision becomes heavier. A young active lake is already hard enough. An ancient sealed one adds a second difficulty, because now access must be balanced against preservation of a setting whose age is one of its central scientific features. That is why the age of these lakes does not stand alone as a fascinating fact to mention and then move past. It directly creates the next problem. Once you accept that some of these environments may have remained apart from the atmosphere or from each other over immense spans, the obvious question is no longer only what is down there. The question becomes how anyone could possibly reach such a place without changing it, misreading it, or damaging the very evidence that makes it worth reaching at all. And that is where the practical part of this story starts to become much less romantic and much more difficult. What makes this topic difficult is that reaching a subglacial lake sounds like a location problem, when it is really a systems problem. From a distance, it can seem almost annoyingly straightforward. Scientists know where some of these lakes are. Radar has mapped them. Satellites have watched the ice surface rise and fall as water moves below. Coordinates exist. The lakes are not hiding in some vague mythical sense. They're on maps, in papers, in planning documents, in environmental evaluations, with names that sound wonderfully matter-of-fact for places so strange. And because of that, the human brain makes a very understandable mistake. It hears known location and quietly upgrades that to accessible destination. But a point on a map is not an entrance. A buried lake beneath hundreds or thousands of meters of Antarctic ice is not reached the way a valley, a cave, or even a deep-sea trench is reached. Before anyone can lower an instrument into that water, they have to move an entire drilling system, a power system, fuel, shelters, sterilization equipment, sampling hardware, people, food, communications, and safety contingencies into one of the least forgiving working environments on Earth. That is the first reason this is harder than it sounds. The lake is there, yes. The route is not. The second reason is scale. It is easy to say, drill through the ice, as if that were a single well-behaved action. In reality, for a deep target like Lake Ellsworth, British Antarctic survey planning involved a hot water drill designed to produce a borehole about 36 centimetres wide through roughly 3.2 kilometres of ice, with the drilling itself expected to take around 3 days. The project documentation also described the combined drilling and auxiliary equipment as weighing about 60 tonnes, with fuel supplies adding roughly another 55 tonnes, requiring heavy lift air transport and extensive field logistics. That is not a small technical package arriving politely in the snow. That is an industrial operation that has to function cleanly, continuously, and far from easy rescue or replacement. A plan like that does not fail because the scientists forgot where the lake was. It fails because every step from the runway onward has to work in sequence, in the cold, under time pressure, with the whole, water, pumps, heaters, generators, hoses, and sterile procedures all behaving exactly as intended. 1 weak link is enough to turn an elegant scientific plan into a very expensive lesson in Antarctic realism. And Antarctica is not generous about weak links. The fieldwork windows themselves are narrow. The Ellsworth planning documents split the project into a long preparation phase and a relatively short access campaign in the austral summer, while US planning summaries for Mercer describe work concentrated between roughly mid-December and early February. That matters because no one is attempting this in a place where you can casually stay another month. Order a replacement part and carry on after a long weekend. Even normal maintenance becomes part of the expedition strategy. Generators have to run for long periods. Fuel must be stored and managed safely. Equipment has to survive transport, setup, operation, and then either retrieval or retrograde. The field camp is not a backdrop to the drilling, it is part of the drilling. If your heat exchangers, pumps, powertrain, communications or water treatment system become unreliable in a remote Antarctic camp, the lake remains exactly where it was, and your mission becomes a lesson in how much civilization you forgot to bring with you. Then there is the slightly rude fact that making a deep borehole in cold Antarctic ice is not like making a tunnel and then walking away to admire it. A borehole is temporary, unstable, and needy. The clean hot water drilling literature makes clear that once lake access is achieved, teams must continue managing the hole as it begins changing immediately, with refreezing and hydrostatic issues shaping what can be done next. In the Lake CEC's drill design, for example, hot water continues to be used during recovery to enlarge and maintain the borehole, and the system has to keep net flow conditions such that borehole water does not enter the lake. That is a surprisingly delicate sentence for a project involving kilometres of hose and tons of machinery. You do not simply open a neat cylindrical door into the ice and proceed at leisure. You create a narrow, melting, refreezing, pressurized passage that has to be monitored and maintained while your scientific window is still open. The passage is not a solved problem. It is a living problem, and it stays one for as long as the lake access attempt continues. Cold itself is only part of the story. The ice sheet is also mechanically awkward. The borehole has to be sufficiently straight and sufficiently usable for instruments to pass through it, without snagging, tilting, or becoming compromised on the way down. That sounds like the kind of engineering detail that belongs in a meeting nobody wants to attend, until you remember that every scientific instrument must survive a descent through a narrow shaft several hundred to several thousand meters long before it even meets the lake. The BAS documentation for Ellsworth and the Wizard papers both treat the geometry and quality of the borehole as major operational concerns, not afterthoughts. Wizard, after completing the subglacial Lake Willans borehole, visually inspected it before deploying instruments. That little detail says a lot. Even after the drilling succeeds, the next question is whether the hole is actually fit to use, not whether it exists, but whether it is trustworthy. A crooked, narrowing, unstable, or imperfectly maintained hole is not just inconvenient. It can end the science before the science begins. This is why the popular solution, just send a robot, is not wrong so much as incomplete in a very expensive way. Of course, scientists would like to send robotic systems. They already do, in limited forms. Wizard used borehole cameras and the micro-subglacial lake exploration device for visual inspection of the borehole and subglacial cavity, and then an array of profiling, sampling, filtration, coring, and sensor systems over the next 3 days. But a robot does not eliminate the main problem. It inherits it. The robot still has to fit through the borehole. It still has to remain clean enough not to compromise the environment. It still needs power, communications, recovery plans, and sufficient reliability to operate after a punishing descent through cold, dark, pressurized conditions. Sending a robot into a subglacial lake is not like tossing a waterproof camera into a swimming pool. It is more like lowering a very fragile, very expensive laboratory through a temporary straw into a place where repairs are theoretical and mistakes may be irreversible. Cleanliness is where the whole problem becomes even less forgiving. If these lakes matter, partly because they may contain ancient chemical signatures, isolated microbial communities, or undisturbed sediments, then the first rule of entering them is that you do not get to arrive dirty. The SCAR Code of Conduct was developed specifically to guide exploration of subglacial aquatic environments, and Antarctic treaty documents later endorsed encouraging its use in planning and operations. That is not bureaucratic decoration. It reflects the basic scientific fact that contamination here is not a side issue. It is central. A single microbe introduced from the surface, a residue from drilling water, a poorly sterilized cable, or a leak from the system can complicate later interpretation of biological and chemical results. The cleaner you try to be, the more complicated the expedition becomes. Every object that enters the borehole becomes part of an environmental argument as well as an engineering one. You're not merely trying to get to the lake. You're trying to get there in a way that does not make your own arrival the biggest event in that lake's recent history. That demand for clean access changes the design of the whole mission. The Ellsworth environmental evaluation described a 5-stage filtration and UV treatment system for the drill water. The wizard work at Willans went further, with instruments entering the lake cleaned using hydrogen peroxide, cables and hoses UV irradiated, and drill water treated through filtration and UV exposure to reduce microbial load. On paper, those sound like sensible measures, and they are. In practice, each layer of cleanliness adds complexity, equipment, procedure, verification, and failure points. A normal drilling operation is already not a peaceful hobby. A microbiologically cautious drilling operation in Antarctica is a choreography. Water must be produced, heated, pumped, filtered, irradiated, delivered and managed while the camp functions, the weather cooperates well enough, and the borehole remains viable. None of these requirements are unreasonable. All of them together make the project very hard. And even if you do everything right, there is still the awkward hydrostatic question. The borehole is full of water. The lake is full of water. The pressures involved do not politely sort themselves out because everyone on the surface has good intentions. The deep, hot water drilling literature after the Ellsworth field season emphasised the need to extract a substantial amount of borehole fluid before lake entry to avoid that borehole water entering the lake. The later clean access drill design for Lake CECs similarly discussed lowering the borehole water level well below the hydrostatic threshold before penetrating the lake to prevent borehole water from flowing into it. That means access is not merely about punching through the final meters of ice. It is about arriving at that final moment with the water column in the hole already under control. You have to think like a plumber, a microbiologist, a glaciologist, and a risk officer all at once. A lake that has waited under ice for vast stretches of time will not reward last-minute improvisation. There are also less glamorous hazards that still matter. Gas and clathrate risks, for example, sound slightly theatrical until you notice that the Ellsworth environmental work treated them seriously enough to assess blowout scenarios on lake entry. The overall risk was summarised as very low, but the point is not that disaster is likely. The point is that even unlikely physical behaviour has to be modelled and planned for when drilling into a long-buried, pressurised, chemically unusual water body. This is what makes subglacial exploration feel so different from ordinary field science. Ordinary field science may ask, how do we get there? Subglacial lake science also asks, what might this environment do the moment we connect two worlds that have been separate? Most of the time the answer is reassuring enough. Sometimes it is not reassuring enough to skip the calculations. The Ellsworth attempt is useful here because it shows in a very human way how little room there is for compounding trouble. BAS called off the 2012 mission after failing to penetrate the lake, and later technical assessment argued that the main and umbilical boreholes may not have linked as planned, with water management and cavity link issues undermining the operation. The lesson was not that subglacial lake access is impossible. The lesson was that a deep clean access attempt through more than 3 kilometres of Antarctic ice can fail because of the interaction between borehole design, water storage, pumping, firn effects, and the mechanics of linking the system the way the plan required. In other words, you can have the science, the funding, the camp, the drilling concept, and the courage, and still lose to the details. Antarctica is not always dramatic in the way films prefer. Sometimes it defeats you with plumbing. Success stories are real, but they also reveal the limitations. Wizard reached subglacial Lake Willans through about 800 metres of ice, and once the borehole was completed, the team had only a brief period for scientific operations, carrying out intensive work over 3 days with a camera, CTD profiler, water samplers, filtration systems, sediment corers, a geothermal probe, and a geophysical string. That was a remarkable achievement. It was also not the same thing as freely exploring a lake in the ordinary sense. It was controlled access through one narrow opening for a finite burst of observations and sampling. You do not roam, you prioritise. You lower one tool, then another, in a sequence that has been argued over long before anyone reaches the field. Every deployment is shaped by the reality that the hole, the weather, the equipment, and the clock are all part of the experiment. So even success looks disciplined rather than expansive. The lake gives you a window, not a waterfront. That narrowness is important because people often imagine exploration as movement. They picture swimming through the water, mapping the basin, turning left into a hidden channel, finding a sediment ridge, maybe meeting the local microbes in a spirit of professional courtesy. But borehole access does not give that kind of freedom. It gives vertical access at one site. Even when a camera or small device enters the cavity, the science is still constrained by tethering, visibility, contamination control, power, and the basic geometry of the opening. You learn a great deal, but from a single puncture point. This is why we reached the lake and we explored the lake are different statements. The first can be true while the second remains only partly true. A lake under Antarctic ice is not resisting us with one grand barrier. It is resisting us with 1,000 constraints, all of which keep access local, careful, and limited. There is a financial and organisational side to this as well, though it need not be spoken about in the dramatic tone usually reserved for budget meetings. Antarctic lake missions are not just science projects. They are multinational logistics exercises with environmental review, transport chains, field safety systems, specialist engineering, and post-field analysis all folded together. BAS's Ellsworth evaluation was a full comprehensive environmental evaluation under the Antarctic Treaty System, and later, Antarctic treaty materials explicitly supported dissemination and use of the Subglacial Aquatic Code of Conduct. That means these projects must clear scientific, technical and stewardship thresholds at the same time. They are not allowed to be merely exciting, they have to be justifiable, and that is probably as it should be. A place buried for so long under so much ice deserves at least as much caution as enthusiasm, even if caution is less glamorous in the documentary trailer. So when people say, with complete sincerity, why can't we just go down there? The answer is that just is doing the dangerous part of the sentence. To reach a subglacial lake, you must transport a heavy clean access drilling system into inland Antarctica, create and maintain a deep usable borehole, treat drilling water, sterilize instruments, control hydrostatic conditions, avoid contaminating the lake, manage a camp and power system in extreme cold, and complete your observations before the access window closes. And if one of those pieces fails, the lake remains unbothered while the expedition becomes a case study. This is not a complaint about the difficulty. It is the shape of the difficulty. The lake is hidden under ice, yes, but it is also hidden behind engineering discipline, environmental responsibility, timing, and the fact that remote field science becomes much less romantic the moment a pump, hose, seal, filter, or generator behaves badly. And even after all of that, another problem waits quietly beneath the practical one, because making contact with the lake is only the beginning of a different kind of danger. You may finally get through the ice, only to face the possibility that the greatest threat to the science is not distance or cold, but us. And that is where the next part of this story naturally moves into the problem of drilling through ancient ice without carrying too much of the modern world down with you. By this point, the main difficulty starts to change shape. Up to now, it might still sound as though the problem is mostly about distance and cold. The lake is far away, the ice is thick, the camp is remote, the machines are large, and Antarctica is not known for being accommodating. All of that is true. But once a drilling team actually begins moving toward a buried lake, another reality appears. The ice itself is not just an obstacle to get through. It is part of the scientific record, part of the environmental risk, and part of the reason the whole mission becomes so delicate. In ordinary speech, people say, drill through the ice, as though the ice were just dead material in the way. In this case, the ice is ancient, layered, physically demanding, and in some places scientifically important in its own right. That changes everything, because the act of getting through it is no longer just mechanical. It becomes an argument about what can pass through that column, what must not pass through it, and what the drill might carry with it all the way down. The first uncomfortable truth is that deep Antarctic ice is not uniform. It is not one neat frozen block, identical from top to bottom, waiting for a hot water drill to treat it politely. The upper and middle parts record snowfall, compression, gas histories and impurities laid down over long periods. Near the base, the conditions change again, and in places like Lake Vostok there is even accretion ice formed by water from the lake refreezing onto the base of the ice sheet. That means the lower section can contain the nearest thing scientists have had to an indirect sample of the buried lake environment, although interpreting that material has always been complicated by contamination concerns. So, when a drill moves downward through ancient ice, it is not crossing a blank zone. It is passing through a layered archive, and the very deepest part may already be scientifically sensitive before the lake itself is even reached. That matters because drilling is never perfectly innocent. A drill does not simply open a hole and leave the surrounding material untouched. It introduces heat, pressure changes, fluids, contact surfaces, motion, friction, and timing constraints. Even hot water drilling, which is widely regarded as the most viable route for clean access under current Antarctic environmental expectations, is still an intervention. The 2016 review on clean subglacial access describes deep hot water drilling as the most viable option precisely because drilling to wet beds in Antarctica has to conform to international stewardship requirements, not because it is magically consequence-free. It is chosen because the alternatives are often worse for contamination control, not because it removes the problem. That is a useful distinction. The preferred method is still a compromise between practical access and environmental caution. Scientists are not choosing between easy and hard, they are choosing between hard and worse. Take the Lake Ellsworth plan as an example, because it shows how much effort is required before the drill even approaches the lake. BAS's environmental evaluation described a system using melted ice water heated to around 90 degrees Celsius, filtered to 0.2 micrometers, and treated with ultraviolet light before being pumped downhole. The drilling concept relied on high-pressure hot water to melt a straight access borehole, with return water recovered and reused through surface tanks and pumps. That sounds practical enough when reduced to a paragraph, but every part of it is there because ordinary drilling behaviour would be unacceptable. You cannot simply pump untreated water from the surface, push it through kilometres of hose, and hope that whatever ends up in the lake can later be explained away in a methods section. The drill water itself must be managed as if it were already part of the experiment, because it is. And then there is the age of the ice. When people hear ancient ice, they sometimes treat that as a poetic phrase, the sort of thing a documentary narrator says over a shot of a horizon. In drilling terms, it is more concrete than that. Deep ice has had time to compact, deform, warm relative to the surface and change crystal structure. BAS's later deep hot water drilling work in West Antarctica noted that drilling to more than 2,000 metres and maintaining holes even for tens of hours required solving outstanding technical issues from earlier failed efforts. That is not merely because the distance is large. It is because thick, old ice behaves in ways that demand careful drilling geometry, water management and timing. Ancient ice is not dramatic because it is old. It is difficult because it is thick, cold, under stress, and not particularly interested in preserving a convenient borehole for you. A hot water borehole is also temporary from the moment it's created. That can be hard to keep in mind because drilling has a natural feeling of permanence. Once we say, a hole has been drilled, the mind assumes the hole now exists in a stable and useful form. In deep Antarctic ice, that assumption quickly becomes dangerous. The borehole begins changing at once. It can narrow, it can refreeze, it can shift operationally from a passage to a problem if water management slips, if the timing stretches, or if the system below does not behave as modelled. The Ellsworth documents and later assessments both make clear that maintaining a usable borehole is part of the job, not something that happens automatically once the nozzle reaches depth. So drilling through ancient ice means creating a passage that the surrounding environment is already trying to take back. You do not cross the ice and then begin the science. Keeping the crossing open is part of the science. This is where ancient ice stops being just a material challenge and becomes a contamination challenge as well. Every meter of borehole wall is contact. Every instrument descending through it passes close to surfaces that have been warmed, wetted, and exposed to whatever your operation has introduced. If the lowest part of the ice includes accreted material related to the lake, or if ancient basal ice carries chemical or biological information that matters, then the drill path is not just a clean corridor, it is a mixing risk. The literature around Lake Vostok is especially instructive here. Studies of accretion ice were important because they offered indirect clues about lake conditions. But later microbiological work also found that fast-frozen lake water samples were contaminated by drilling fluid, and drilling fluid remains one of the main recognized sources of chemical and biological contamination in deep ice core and lake water sampling. In other words, the route down can alter the evidence before the lake is even sampled directly. Lake Vostok has been the long-running cautionary tale for exactly this reason. The Russian drilling program used a hydrocarbon-based drilling fluid mixture, and official Antarctic treaty environmental documents spent considerable effort discussing the likelihood of that fluid penetrating through ice, migrating through structures near the bed, and what would happen if contamination occurred. One of those assessments argued that direct penetration into the lake was practically excluded under the assumed conditions, with modelled penetration through the ice of less than a metre over the first millennium, while also acknowledging contamination risks from hydrofracturing and other scenarios. That is an extraordinary sentence to have to write in science at all. Imagine explaining to almost any other field that your method is acceptable, partly because the contaminant might take 1,000 years to move less than a metre. It tells you something important about the environment. When the target is ancient, inaccessible, and hard to sample cleanly, researchers are forced into very careful forms of reassurance. None of this means the Vostok scientists were careless. It means they were working at the edge of what older drilling methods could plausibly manage. The problem is not solved merely by saying we will be careful. Hydrocarbon drilling fluids help keep deep boreholes from freezing shut, but they also create obvious concerns when the goal is uncontaminated sampling. The 2021 Annals paper on Lake CECs notes explicitly that refrozen lake water samples from Lake Vostok were later recovered using an ice core drill, although contamination from the hydrocarbon-based drilling fluids remained an issue. That single point captures why ancient ice makes drilling so awkward. The same system that allows access can compromise interpretation. The same fluid that makes the borehole possible can make the sample suspect. Once that trade-off becomes visible, the whole romance of going down to the lake starts to look much more like a long exercise in choosing the least damaging imperfection. The cleaner hot water approach was developed partly as a response to exactly that problem. Wissard and Ellsworth planning both treated drill water as something that had to be filtered, UV treated, and carefully managed before it ever went near the lake. Wissard-related descriptions also note that instruments entering the lake were cleaned with hydrogen peroxide, and that cables and hoses were UV irradiated, again because anything travelling through the borehole could become a contamination route. That sounds rigorous, and it is. It is also revealing. Even when the drilling fluid is just water derived from the ice sheet, scientists still do not trust it by default. It has to be processed, monitored, reused carefully, and prevented from flowing into the lake at the wrong moment. Ancient ice is therefore not drilled with a simple mechanical tool. It is drilled with an entire cleanliness system attached. Pressure control makes the situation even more awkward. A subglacial lake sits under a very different pressure regime from the surface camp above it. The borehole has its own water column. The lake has its own conditions. The final breakthrough is not just a dramatic instant of success. It is a hydrostatic event that has to be managed so that borehole water does not enter the lake. and lake water does not behave in unexpected ways. Post-Ellsworth technical assessments stressed that a substantial amount of borehole fluid has to be extracted before lake entry to avoid forcing borehole water into the lake. The Lake CEC's clean drill design discussed the same logic, lowering the borehole water level below the hydrostatic threshold before penetration. So by the time the drill nears the deepest ice, the mission is no longer about melting downward. It is about getting every water level, every pressure relationship, and every timing step right. If you drill through ancient ice carelessly at the last moment, the damage is not symbolic. It is physical. What makes this especially frustrating is that ancient ice often contains the very clues you do not want to disturb. The lower ice over a subglacial lake can preserve signatures of how the lake exchanges heat, freezes onto the ice base, and changes chemically over time. In Vostok, accretion ice became a major scientific target because it offered one of the few available ways to infer lake conditions without open water exploration. Yet official documents around Vostok also describe molecular biological studies of that accretion ice, while discussing contamination risk from borehole fluids and bacteria associated with the drilling environment. So even the material that seems like a convenient compromise between no access and direct access is not easy to interpret cleanly. The drill does not merely pass through history, it can rewrite the margins of that history if the operation is not designed with extreme restraint. There is a more ordinary mechanical problem as well, and it deserves attention because these missions often fail in ordinary ways wearing impressive jackets. Ancient ice at depth is not guaranteed to let your equipment behave well. Boreholes can fail to link as intended. Pumps can underperform. Water storage assumptions can turn out to be wrong. Firn conditions in the upper layers can complicate circulation and recovery. The assessment of the failed Ellsworth field season argued that hot water drilling remained the only feasible scheme for clean access, while also concluding that substantial technological and methodological advances were still necessary for successful research beneath thick ice over 2 kilometers deep. That is an important sentence because it cuts through the fantasy that we already know how to do this reliably and are merely waiting for the next brave team. We know how to attempt it. Reliability at great depth under clean access rules is still difficult. Ancient ice is not only old, it is an active filter against overconfidence. Then there is the simple fact that the deeper the ice, the longer the drill path acts like a contamination corridor. Even when everything is sterilized to the best practical standard, every hose, cable, probe and sensor has to descend through kilometers of shaft before it reaches the target. That long path gives time for temperature shifts, for borehole walls to change condition, for refreezing to narrow tolerances, and for any imperfection in cleaning to matter more than you would like. The SCAR code of conduct exists because Antarctic subglacial aquatic environments are recognized as unique and vulnerable, and because exploration has to be planned around that vulnerability rather than treated as standard field access. Ancient ice makes that vulnerability longer. It stretches the route between your controlled surface procedures and the environment you hope to leave mostly unchanged. The deeper the lake, the more meters there are in which small lapses can become meaningful. At this stage, the human instinct is to simplify again. Why not use a thermal probe and let it melt its way down cleanly? Why not drill fast and sample before the hole changes? Why not accept a little contamination and sort it out statistically later? These are understandable thoughts, but the Antarctic subglacial literature repeatedly shows why they are not satisfying answers. Some alternative probe concepts have been judged impractical or environmentally problematic in specific contexts. Fast drilling does not remove hydrostatic control, sterilization or recovery challenges. Statistical cleanup is not comforting when you're looking for sparse microbial signals or subtle chemistry in an environment that may have had no recent contact with the surface world. Once contamination becomes plausible, the interpretation of life, nutrients, organics, or unusual cells becomes much more fragile. That is why drilling through ancient ice is not just an engineering exercise. It is evidence management from the first meter to the last. There is also a quiet ethical pressure here that makes the practical difficulty feel heavier. A young surface lake can be resampled, revisited, and compared against nearby sites with relative ease. A deeply buried Antarctic lake may offer one narrow access point after years of planning, immense cost and international review. If the first direct contact is compromised, there may not be a simple second chance. A mission can be postponed for a season, abandoned, redesigned, or left with ambiguous results that are argued over for years. That is one reason ancient ice feels almost adversarial, though that word flatters us by making it sound personal. Really, the ice is just indifferent. It has preserved a difficult environment for a very long time, and our methods have to be better than our impatience. The older the record below, the less tolerance there is for saying, well, we mostly got away with it. What all of this adds up to is something more specific than drilling is hard. Drilling through ancient ice is hard because the ice is thick, because the borehole is temporary, because pressure must be controlled, because the lower ice may itself be scientifically valuable, because the route down can transport contamination, and because the lake at the bottom may be important partly for having remained separate from us. That combination is what makes the whole task feel so unforgiving. You're not only making a hole, you're creating the one path through which modern machinery, modern microbes, modern chemistry, and modern mistakes can travel into an environment that may have been physically isolated for extraordinary spans of time. Once that is clear, the next problem almost introduces itself, because after all the effort of drilling downward, the most troubling possibility is that the greatest thing we deliver to the lake is not knowledge, but ourselves. At this point, the whole subject becomes more uncomfortable in a very precise way. Up to now, the danger may have sounded mostly physical. The ice is thick, the weather is hostile, the distance is absurd, the borehole wants to freeze, the equipment has to keep working in a place that is not interested in being useful. But once a team gets serious about touching a buried lake, the most troubling problem is no longer simply whether they can arrive. It is whether their arrival ruins the thing they came to understand. That is not an exaggerated fear. It is built directly into the modern rules and planning around subglacial research. In 2017, the Antarctic Treaty Parties endorsed SCAR's Code of Conduct for Subglacial Aquatic Environments as current best practice, explicitly recognising that these environments may contain exceptional and potentially unique microbiological communities and may be harmed by the introduction of non-native microbes or other contaminants. The British planning documents for Lake Ellsworth made the same point in plainer field language, treating the lake as a pristine aquatic environment where possible damage and contamination had to be minimised or eliminated. That is a very different tone from ordinary drilling. It means contamination is not a side risk. It is one of the main scientific facts of the mission, and contamination, in this setting, does not mean only the dramatic version people imagine. It does not require a ruptured fuel tank or some obvious cloud of pollution spreading through the water, while everybody on the surface begins using very tense voices. In a buried lake, contamination can be almost embarrassingly small. A few stray microbial cells, fine particles, trace chemicals from a hose, a seal, a lubricant, or a drill fluid, residue left on a cable, organics carried in with the water used to make the borehole. That is why the standards become so severe. The WISA drill design papers cite the National Research Council benchmark that the number of microbial cells on or in materials introduced into the environment should not exceed that of the basal ice being passed through. That is a very strict threshold, and it tells you everything about the scale of the problem. The danger is not merely bringing obvious dirt into a hidden lake. The danger is adding even a small amount of modern biological or chemical material to a place where the background levels may already be extremely low and where the signs of indigenous life may themselves be sparse. In a place like that, a little contamination can stop being little. This is why older deep mechanical drilling methods became so controversial around subglacial lakes. To keep very deep boreholes open, ice core drilling typically relies on dense drilling fluids, often hydrocarbon-based. Those fluids are practical in one sense because they help balance pressure and prevent the hole from closing, but from the perspective of a hidden aquatic environment, they are almost offensively impolite. A 2016 review on clean subglacial access states it very clearly. Traditional drill fluids can host abundant microbial life and create a high probability of both biological and chemical contamination of the subglacial environment and of the samples brought back to the surface. The Mercer Lake Access paper repeats the same point and directly notes that mechanical drilling using hydrocarbon-based fluids can contaminate both ice core and subglacial water samples as well as the subglacial environment itself. That is why hot water drilling, for all its trouble, became the preferred clean access approach. It is not because hot water is easy. It is because sending hydrocarbon-based drilling fluid toward an ancient lake is a very poor way to preserve trust in whatever you later claim to have found. Lake Vostok is the long-running example that keeps everyone honest here. For years, it represented both the dream and the warning. It was one of the most compelling targets on Earth, and also one of the clearest demonstrations of how easily access and interpretation can become entangled. Studies of the Vostok drilling fluid found bacterial diversity within that kerosene-based fluid, including organisms associated with hydrocarbon degradation, which is exactly the kind of detail that makes later biological claims much harder to read with confidence. The broader Clean Access review notes that after mechanical penetration of Lake Vostok, lake water rose into the borehole and was later frozen and cored, but the general problem remained. A drilling system that depends on fluid known to carry microbial and chemical contamination is fundamentally difficult to reconcile with the idea of pristine sampling. This does not erase the scientific value of that work. It simply means that every result arrives with an argument attached. The lake may be ancient, but the route into it can add very modern noise. Even the cleaner method is not clean by default, and that is one of the hardest parts for people to accept. A hot water drill sounds almost reassuring compared with a hydrocarbon borehole fluid. Water feels natural. Water sounds innocent, but the water used in drilling is still a carrier. If it is not filtered, sterilized, and managed carefully, it can still bring cells, particles, and dissolved material downward. That is why the clean hot water drilling literature stresses that the drill water must be ultra-filtered, UV-treated, and pasteurized before it is used to create the access hole. The Lake Ellsworth Environmental Evaluation described the planned drill water as melted ice water, heated to about 90 degrees Celsius, filtered to 0.2 micrometers, and UV-treated specifically as part of the contamination control strategy. In the Mercer campaign, the clean access components inherited from Wissard included submicron particle filtration and high-intensity UV treatment of the drilling water, with contamination monitored in real time through sampling ports in the system. The point is easy to miss because it hides inside engineering language. The hole is not made by water. It is made by processed water that has been treated as a scientific instrument. Then the problem spreads outward from the water to everything else. The borehole is not the only thing entering the lake. Every cable, hose, probe, tether, sampler, corer, camera housing and deployment frame becomes a possible route for contamination. That is why the Ellsworth plans devoted so much attention to microbial control on engineered structures, including the wellhead, drill hose, sampling probe, tether, corer, and thermistor string. The same documents describe a UV collar at the wellhead, gate valves functioning as an airlock, and repeated sterilization procedures for surfaces passing into the borehole. Wissard's drill system design paper says the exterior of hoses and cables was physically cleaned using dilute hydrogen peroxide, precisely because all materials entering the subglacial environment had to meet the clean access standard. The Willans Microbial synthesis paper adds that instruments entering the lake were cleaned with a 3% hydrogen peroxide solution, and that all cables and hoses were UV irradiated. None of this is decorative caution. It is an admission that a lake does not care whether contamination arrives by dramatic drill fluid or by an ordinary-looking cable skin. To the lake, modern is modern. A person might assume that once the equipment is sterilised at the surface, the problem is solved. Unfortunately, the borehole itself becomes a contamination corridor. It is kilometres long in some cases, water-filled, changing as drilling proceeds, and in constant contact with the very surfaces through which all later instruments must travel. That means contamination control is not a single cleaning event at the start of the mission. It has to be maintained across the whole descent. The Mercer paper explains that Wizard monitored contamination potential in real time through a series of sampling ports placed throughout the drill system, so that possible contamination sources could be identified before breakthrough. Forward contamination could be minimised, and samples brought back to the surface could be checked against surface compromise. That is a remarkable thing to need in field science. You're not simply trying to obtain a sample, you're trying to build a chain of custody between a buried lake and your laboratory, with enough monitoring along the way that you can later argue, honestly and in public, that the life or chemistry you observed did not come from your own plumbing. This is also why contamination is not only biological, it is chemical and physical as well. Hydrocarbon fluids are the obvious example, but even with clean hot water drilling there are still particles, dissolved substances, residues from manufacturing, and materials compatibility issues to worry about. The Ellsworth plans, for instance, discuss material selection, in part because hard materials such as titanium are easier to clean and also help with trace iron work, which is another way of saying that even the composition of the hardware can matter to the chemistry being measured. When a mission is looking for subtle geochemical signals or low biomass microbial communities, a trace contaminant is not a cosmetic defect. It can move the entire interpretation. A few unexpected organics or a few modern cells in an oligotrophic environment can look alarmingly like discovery. That is an inference, but it is the entire logic behind the treaty guidance, the filtration systems, the sterilisation routines, and the requirement to monitor contamination before and after lake entry. There is another uncomfortable feature of this problem. The more interesting the lake is, the less contamination you can tolerate. A connected, active subglacial water system is already difficult enough because it still represents an environment people cannot sample casually. But a more isolated lake, one that may preserve long separate water, sediments and microbial signatures, raises the standard even further. The treaty resolution endorsed the Code of Conduct because these environments may support unique communities and may be harmed by introduced microbes or contaminants. The Clean Access Review goes even further in practical terms by assuming, unless there is site-specific evidence otherwise, that drilling to the base of Antarctic ice may encounter liquid water that forms part of a protected drainage network. In plain language, the default assumption is caution. Scientists are asked to behave as though the water they reach matters before they have even proved exactly what is in it. That is frustrating if you want fast exploration, but entirely sensible if the first uninvited cells to enter an ancient lake turn out to be ours. What makes this especially maddening from a scientific point of view is that contamination can mimic success. Suppose a team drills into a lake, retrieves water, and detects microbial DNA, cells, metabolic products, or a faint chemical signature that looks biologically important. In a surface lake, you would already be cautious. In a buried Antarctic lake, caution becomes almost the whole exercise. Was that signal native to the lake? Was it introduced during drilling? Did it come from the drill water, the hose surface, the sampling bottle, the cable, the wellhead, the field lab, or some component that was cleaned but not clean enough? This is not a hypothetical worry invented to make the field sound more dramatic. It is exactly why Wizard and Salsa used real-time contamination monitoring, why Ellsworth built microbial control into the design stage, and why older fluid-based access methods are so scientifically awkward. The discovery is not secure unless the pathway to the discovery is secure as well. There is also a human temptation hiding inside all of this. Once a mission has spent years planning, shipping equipment, training personnel, and establishing a field camp on the ice, there is enormous pressure for the lake access to count. Not in an improper sense, simply in the ordinary emotional sense that everyone wants the effort to lead somewhere. That makes contamination discipline even more important, because the most dangerous moment is often the moment of breakthrough, when success is suddenly close and the urge to proceed can become stronger than the urge to be patient. The Lake Ellsworth materials are revealing here. They include explicit concern about borehole water being forced into the lake and discuss methods intended to minimize the amount of borehole material entering the target environment. That is the sort of tale that never appears in the public imagination of exploration, yet it may be one of the most important details of all. A hidden lake is not only vulnerable to the big mistake, it is vulnerable to the understandable shortcut taken near the end of a hard job. By the time all of this is taken seriously, contamination stops looking like a technical sub-problem and starts looking like the central discipline of the whole enterprise. It shapes what drill can be used, what materials can touch the lake, how the water is processed, how the borehole is managed, how the instruments are cleaned, how the samples are interpreted, and how confident anyone can be afterwards. It also explains why true exploration remains so limited. The wider and more mobile your access system becomes, the more surfaces, pathways, and failure points you create. Freedom of movement sounds attractive until every extra meter of tether and every extra component becomes another possible way to carry the surface world downward. That is why subglacial lake work often looks so restrained. It is restrained because restraint is part of the data quality. And once that is clear, the next part almost writes itself, because all of this caution has to be enforced by hardware, filters, UV systems, pressure controls, sterilized hoses, straight boreholes, sealed deployment paths, reliable pumps, and instruments that still have to function after passing through all of that. The contamination problem does not stay in the realm of microbiology for very long. It turns into an engineering problem immediately, and in Antarctica, engineering problems tend to become survival problems for the machines themselves. By now, the trouble has shifted away from maps and into machinery. Up on the surface, it is still possible to talk about a subglacial lake as a destination. There is a drill site, there is a camp, there is a target below, but for the machines, none of that feels simple. A machine sent toward a hidden lake under Antarctic ice does not get to do one job. It has to survive shipping, assembly, sterilization, deployment, freezing conditions, narrow geometry, pressure changes, uncertain visibility, awkward recovery, and sometimes a ticking clock set by the borehole itself. The wizard hot water drill system is a good example of how complicated this becomes. It was not a single clever device, but a coordinated system with 4 low-pressure pumps, 2 hot water generation units containing 6 diesel burner modules, multiple winches, a traction drive, and large numbers of sensors, all managed through one control setup. That does not sound like a neat little robot being lowered into mystery. It sounds like a moving industrial ecosystem that has to remain disciplined while standing on ice. And even then, the drill is only the beginning. Once scientists have a borehole, they still need instruments that can travel down it and work properly when they arrive. In practice, that means cameras, CTD probes, water samplers, filtration units, sediment corers, geothermal probes, geophysical strings, and sometimes more specialized systems, all taking turns through one narrow access route. At Subglacial Lake Willans, the team deployed a downhole camera, a conductivity temperature depth profiler, a Niskin bottle, an in-situ filtration unit, 3 kinds of sediment corers, a geothermal probe, and a sensor string over 3 days of tightly managed operations. At Mercer, the instrument sequence was also carefully planned, and repeated reaming was needed to maintain access while operations continued over about 10 days. This is part of why the machines struggle. They are not exploring in the usual sense of wandering around freely. They are queuing politely one after another through a borehole that is changing while they use it. The cold is not just very cold either. which is how people usually speak when they have no intention of working in it. The water at the target is often very close to its own freezing point, and pressure is part of the reason it remains liquid. At Lake Willans, the minimum measured water temperature was about -0.55 degrees Celsius, consistent with a pressure of roughly 7.019 megapascals. Mercer showed similarly narrow margins, with lake water averaging about -0.74 degrees Celsius, and borehole conditions changing measurably after reaming. That means the machine arriving at depth is not entering some comfortably stable underwater room. It is entering a near-freezing high-pressure environment where small differences in temperature matter, where the borehole can warm or cool after operations, and where the boundary between ice and liquid is not a dramatic wall, but a sensitive interface. That is hard on equipment in a quiet, persistent way. Sensors have to remain accurate. Housings have to remain sealed. Lights, cameras, connectors, and moving parts all have to keep working when the environment is only just allowing water to stay water. This is why probe designs start to look a little overqualified, and with good reason. The Ellsworth probe concept, for example, was about 5.17 metres long, 0.20 metres in diameter, and built around multiple gas-filled pressure cases with titanium outer sections. Power was to be supplied from the surface as high-voltage direct current through a tether, while the probe also carried onboard systems for sensing, sampling, logging, and backup operation. The treaty-related environmental documents for Ellsworth describe real-time data return, onboard microprocessors and data logging for continued operation during communications failure, power from both tether and onboard batteries, and redundant probe deployment in case of failure or contamination. Those details are revealing. They tell you that the machine is expected to lose things. It may lose communication, it may lose some power margin, it may suffer contamination concerns. It may need redundancy because nobody wants to spend years preparing a clean access mission only to have a single pressure case, cable fault, or electronics issue end the entire science program. Then there is the tether, which sounds harmless until you think about what it is being asked to do. In Ellsworth planning, these tether-carried optical fibres and electrical cables inside an aramid polyester structure with a polyurethane outer layer that could be cleaned, and that helped prevent microbial egress from inside the tether. It also had to handle lowering the probe at around 1 metre per second, remain mechanically trustworthy, preserve communications, deliver power, and still behave during deployment through sterile interfaces, valves, airlocks, and handling systems. A tether in this context is not just a rope with ambitions. It is power line, data line, lifeline, contamination barrier, and recovery path all in one. If it snags, abrades, twists badly, or suffers a communications fault, the consequences are not minor. The probe may still exist, but the mission may no longer be under proper control. And because these systems go down one narrow hole, there is very little room for improvisation once the hardware is committed to the descent. People often imagine that once a machine reaches the water, the hard part is over. That would be a comforting story, but the papers do not support it. The borehole itself remains unstable as a working environment. At Willans, the team specifically recommended supplying enough heat to the top of the borehole to keep it from freezing. In the same paper, they estimated that even a small amount of warm drill water could prevent an ice layer from thickening too quickly near the surface, which tells you how eager the system is to close again if heat management slips. Mercer required 3 reams after breakthrough to maintain access during operations lasting about 10 days. The newer Beamish system on Rutford showed what improved engineering can do, successfully drilling holes up to 2,154 metres deep and maintaining them for up to 36 hours, while also creating cavities interlinking boreholes about 230 metres below the surface to support recirculation during deep drilling. All of that is impressive. It is also a reminder that the hole must be actively kept useful. The machine is not descending through a settled tunnel. It is descending through a passage that survives only because the surface system keeps fighting for it. The narrowness of the access path creates another problem. which is that instruments have to be designed around borehole limits before they are designed around the lake itself. The sediment coring literature says this quite plainly. One of the main limitations on obtaining longer subglacial sediment cores is the radial size restriction of the hot water borehole. The Probe Technology Review makes a similar point from another angle, noting that different lake projects are shaped by the depth and temperature of the overlying ice, the drilling methodology, the drill fluid, the dimensions of the access hole, and how long it can be kept open. That means a machine is not built only for the science it wants to do. It is built for the door it has to pass through. A beautiful, capable instrument that is slightly too wide, too delicate, too difficult to sterilize, or too awkward to recover is not a solution. It is a workshop ornament. In a subglacial lake mission, borehole geometry is the first manager every device must answer to. That same geometry is why fully free-swimming exploration keeps sounding better in imagination than in engineering. The literature on probe technology shows just how integrated some of these systems have to become. For Lake Vostok, one proposed probe system involved modular instruments sealed within a heated cylindrical transportation unit, lowered through a mechanically drilled borehole, while trying to avoid contact with exogenous microbial communities in the drilling fluid. For Willans, the extended access time allowed multiple packages to be lowered one after another rather than forcing everything into a single highly integrated probe. For Ellsworth, by contrast, the probe itself combined pressure cases, samplers, cameras, lights, sensors, and communication systems into one slender form. None of those designs are casual. They're all responses to the fact that deep ice, limited open time, and contamination control force scientists to pack functions tightly, strip out waste, and treat every added component as a possible liability. A machine under Antarctic ice does not get to be generous with space or casual about failure. Visibility makes the machines look less heroic as well. Cameras sound decisive in the abstract. Surely once a camera enters the lake, clarity will arrive. Yet Willans showed that the water was turbid, and remained turbid even after filtration through 0.45 micrometer filters. The borehole camera there was useful enough to inspect the hole and image the soft sediment at the lake bottom, but the researchers also note that increasing turbidity near the bottom made it difficult to determine the exact depth to the ice base visually. At Mercer, imagery of the lower ice and lake interface was informative, but borehole wall conditions were described as dynamic and influenced by debris, conductivity gradients, borehole diameter, and mixing in the water column. So even the simplest dream of exploration, the dream of seeing clearly, does not arrive on schedule. The machine may carry lights, lenses, and sensors, but the environment still decides how much of itself it is willing to show. Sometimes, the first thing the camera documents is not a landscape but the limits of the camera. Recovery is where the tone becomes even less glamorous. In the Ellsworth Environmental Evaluation, BAS explicitly notes that hot water drilling allows reaming around potential stick points to release drill equipment effectively, but that if the probe or corer itself becomes stuck, recovery is not easy. And if equipment is lost in the lake, there is no contingency plan to recover it. That is one of those sentences that should be read twice because it strips the romance off the problem very effectively. A machine lowered into a subglacial lake is not operating in a place where mechanical trouble is an inconvenience. It is operating in a place where mechanical trouble may become a permanent addition to the lake. That risk pushes design towards simplicity, robustness, and caution, which is sensible but restrictive. It also means the people controlling these systems must spend a great deal of their effort preventing trouble rather than improvising elegantly once trouble begins. That is not a failure of imagination. It is what responsibility looks like when the nearest service bay is mostly weather. Even the software philosophy reflects this environment. The Wizard instrumentation paper notes that the control system was designed around commercial off-the-shelf components. Modularity, rapid deployment, redundant manual operator controls, and a deliberately low degree of automation so the system would not depend too heavily on software control loops in its first season. That is a striking design choice in an age that likes to pretend more automation always means more progress. Here, too much automation can become another failure pathway. In the Antarctic field setting, a human operator with manual authority may be preferable to a beautifully clever loop that misbehaves at the worst possible moment. The machines struggle in extreme cold and pressure, partly because this is not just an electronics problem, it is a trust problem. What do you trust far from repair, far from spare parts, and far from a second attempt? Very often the answer is a system that is smart enough to help and simple enough to rescue. That rescue idea becomes literal once you look at autonomous sonde concepts. A 2023 study on recovering a frozen subglacial exploring sonde begins with a blunt premise. Autonomous sondes risk becoming frozen into the ice if heating fails. The paper then proposes a hot water rescue drilling system that would follow the cable and melt surrounding ice, with theoretical requirements of about 25 litres per minute and pressure greater than 4.2 megapascals to free a sonde at 500 metres depth. That is almost darkly amusing in a technical way. We are already discussing machines built to explore hidden water under the ice, and now we also need machines designed to rescue those machines from the ice if they stop behaving. But the point is serious. A robotic solution does not abolish the problem of the environment. It merely changes the shape of the failure. Under Antarctic conditions, every machine carries the possibility of needing another machine behind it. And that leads to the final difficulty, which is that all these machines are working inside an environment that punishes delay. The Probe Technology Review notes that in some configurations the access time before the lower part of the borehole freezes is limited to hours, while Willans and Mercer showed that repeated reaming and careful sequencing are needed to preserve a working interval even in successful campaigns. So every device is built not only for cold and pressure, but for urgency. It must work after sterilization, after transport, after handling, after descent, and before the hull changes too much. It must not take too long to deploy. It must not create unnecessary contamination. It must not be too awkward to retrieve. It must survive a physical environment that is narrow, near freezing, pressurized, turbid, and mechanically temporary. By the time all that is true at once, the machinery begins to look less like a fleet of conquering tools and more like a group of specialists trying to do careful work while the room itself keeps rearranging. So the machines struggle not because Antarctic engineers are underprepared, or because scientists have somehow forgotten how to build instruments. They struggle because the assignment is unreasonable in a very specific way. Build a system narrow enough for the borehole, clean enough for a pristine lake, strong enough for pressure, light enough to handle, smart enough to collect useful data, simple enough to trust in the field, recoverable enough not to become permanent litter, and fast enough to finish before the access path changes. That is a very tall order for any hardware, especially in a place where even success often means a brief and tightly managed glimpse rather than free movement. And once you see that clearly, the next part of the story follows naturally, because the machines are only one part of the difficulty. The setting itself keeps changing the rules through remoteness, darkness, and isolation, until even a perfectly designed instrument would still find that the environment has its own way of saying not so fast. By the time the machines are ready, it becomes tempting to think the rest of the problem is mostly technical. Build the drill, clean the system, lower the instruments, collect the samples, and keep everyone warm enough to continue making responsible decisions. But this is where the setting itself begins to take over. Distance, darkness, and isolation do not merely make the work more difficult around the edges. They change the entire meaning of the work. A normal field site is a place you can approach, revisit, compare with neighbouring places, and support from nearby infrastructure. A subglacial lake in Antarctica is the opposite of that. The United States Antarctic Program describes Antarctica plainly as Earth's highest, driest, coldest, windiest, and most remote continent, and even the large national programs depend on major logistical systems, just to keep stations and field camps running. BAS says vast remote areas of the polar regions would otherwise be inaccessible without aircraft, which is a neat way of admitting that Antarctica remains stubbornly large even before you start drilling through it. That remoteness matters first at the human level. People hear remote field camp and often imagine something rugged but manageable, perhaps like a difficult mountain camp with better jackets. Antarctic logistics are more demanding than that. The Ellsworth planning documents described a field operation that required heavy lift aircraft, fuel, shelters, drilling equipment, generators, and months of preparation for a comparatively short access window in the austral summer. BAS's overview of field seasons makes the same point in broader terms, noting that ships and infrastructure spend months resupplying stations and field operations for the year ahead. The Subglacial Lake team is therefore not simply visiting a site, it is bringing a temporary working world with it, because there is no nearby town, no workshop down the road, and no casual backup plan waiting over the horizon. Distance turns every missing part, every equipment fault, and every weather delay into a larger event than it would be almost anywhere else on Earth. And that is only the surface distance. Once a lake is buried beneath hundreds or thousands of meters of ice, the remoteness becomes vertical as well as geographic. A person standing above Lake Willans is still around 800 meters of ice away from the water below. Mercer lies around 1,200 meters down, and some East Antarctic targets lie beneath far more. Wizard reached Lake Willans and then worked through a single borehole for 3 days, while the Mercer campaign maintained access with repeated reaming during a roughly 10-day science window. Those are extraordinary successes, but they also show how distance changes the shape of observation. Scientists do not move naturally into these environments. They operate through a narrow vertical line. All knowledge arrives through that line, and if that line becomes unusable, the lake effectively recedes from reach again. This is not like standing on the shore of a lake and deciding which direction to walk. It is like trying to understand an underground room while looking through one temporary shaft in the ceiling. That narrowness also means there is almost no surrounding context. In ordinary exploration, you can often improve understanding just by moving sideways. You walk a little farther along the shoreline. You sample another inlet. You compare one patch of sediment with another. In a subglacial lake, the first sample point may be the only sample point you can realistically reach in that season. A camera lowered into one borehole can tell you what is directly below or just around that opening, but it cannot instantly reveal the full shape of the basin, the gradients across it, the path of inflow and outflow, or whether the place you sampled is typical or unusual. That is why reaching a lake and exploring a lake are still very different things. Distance has removed the ordinary method of learning by movement, and without movement everything becomes more local, more inferential, and less complete. Darkness changes the story just as much, though in a different way. Antarctica on the surface already lives by extreme light cycles. BAS notes that the continent experiences months of darkness in winter, while official Australian Antarctic information says that at the poles there can be several months of 24-hour daylight in summer and complete darkness for several months in winter. That affects human operations, timing, transport and morale on the surface. But for subglacial lakes, the more important darkness is permanent. NASA's astrobiology coverage of Lake Willans and Bass's work on isolated subglacial lakes both stress that these environments have no access to sunlight. Any life there cannot rely on photosynthesis and must instead survive on chemical energy sources. So there are really 2 layers of darkness in this story. Antarctica has a seasonal darkness above, and the subglacial lake has a total darkness below. One challenges the expedition, the other defines the environment. That permanent darkness matters because it removes one of the most helpful tools humans usually depend on when they enter a new place. Vision is not just about cameras, it is about orientation. In a normal landscape, seeing helps you understand size, slope, texture, hazard, and relation. In a buried lake, there is no ambient light, no horizon, no natural shoreline view, and often no clear water waiting helpfully for a lens. At Willans, the water was turbid enough that even visual work near the bottom became more difficult. An earlier ice stream borehole work noted that additional clean water sometimes had to be pumped through the system, simply to reduce turbidity enough for useful camera imaging. So darkness below the ice is not solved by bringing a light. A camera can illuminate a small region, but it does not restore the natural context that open-air exploration depends on. It gives you a lit patch inside a very large unknown. There is something quietly frustrating about that, because modern culture tends to believe that once a camera arrives, the mystery has basically agreed to cooperate. We are used to seeing difficult places become legible the moment the lens turns on. Subglacial lakes refuse that bargain. The water may be clouded by disturbed particles, the field of view may be narrow, the cable may limit movement, and the camera may be showing a highly local scene rather than a representative one. A camera lowered through a borehole does not produce a full landscape, it produces evidence from one constrained position. That is still valuable, of course. The first view below the ice at Willans was important precisely because so little had ever been seen directly there before. But darkness changes the standard of what seeing means. In open environments, seeing often leads quickly to mapping. In subglacial lakes, seeing may only confirm how much remains outside the beam. Isolation then adds a third layer, and this one reaches beyond distance and light into the basic logic of support. On the surface, research stations have satellite links, radio systems and field communications, but BAS also notes that in Antarctica, communications can be a matter of life and death, and that systems can be disrupted by weather or atmospheric phenomena. USAP's participant guidance describes Antarctica as an extreme, remote environment where medical facilities are limited. Those 2 points may sound like ordinary field safety language, but they become much heavier once a team is drilling into hidden water. Isolation means there is no easy escalation path if something goes wrong. If equipment fails, the delay is larger. If someone becomes ill, the response chain is more demanding. If communications degrade, decision-making gets narrower at the exact moment when the operation most needs clarity. A project like this is not happening next to robust infrastructure. It is happening at the edge of what infrastructure can temporarily be made to do. That isolation affects judgment as much as logistics. In a normal laboratory, a puzzling result can often be checked by repeating the test, consulting nearby colleagues, or opening another instrument. At a remote Antarctic drill site, the borehole is changing, the weather may be tightening, the equipment queue is fixed, and every deployment has to justify its place in the schedule. There is much less room for leisurely correction. The Mercer and Willans operations show this clearly. Once the hole was open, the teams followed tightly structured sequences of camera work, profiling, water sampling, filtration, coring, and sensor deployment within limited working windows. Isolation compresses choices. It does not merely make the site lonely, it makes every decision more expensive because alternatives are harder to reach. This is also why comparisons to space exploration are so common in subglacial lake science. NASA's astrobiology program explicitly treats Antarctic subglacial lakes as useful analogues for icy worlds because they are cold, dark, nutrient-limited and hard to access. That comparison is not just a public relations flourish, it reflects a real operational similarity. When an environment is so isolated that you cannot move freely, cannot easily repair hardware, cannot casually return for another look, and must preserve a pristine setting while gathering meaningful data, the mission starts to resemble a planetary exercise more than ordinary fieldwork. Antarctica is still on Earth, of course, and that fact is doing a great deal of useful work for everyone involved. But in practical terms, these lakes already teach scientists what it means to operate where access is scarce. Visibility is limited, and disturbance itself can become the main scientific mistake. The isolation is scientific as well as operational. BAS's work on buried Antarctic lakes notes that many of these environments have been isolated from the atmosphere, and, in some cases, from one another for very long periods. That means the scientist is not only isolated from the lake has been isolated from the scientist's world. It has not developed under sunlight, seasons in the usual sense, surface food webs, or ordinary contact with weather and biology from above. This matters because it limits the usefulness of familiar assumptions. We cannot simply think, well, lakes usually behave like this, so this one probably does too. A subglacial lake may stratify differently, circulate differently, host life differently, and preserve sediments differently precisely because it has been so cut off. Isolation changes the environment before we ever arrive, and then changes our ability to understand it once we do. There is another effect that distance, darkness, and isolation produce together, and it is subtler than the others. They make uncertainty accumulate. In easier places, uncertainty can often be chipped away by adding more observations quickly. Walk another kilometre, return tomorrow, bring another team. In a subglacial lake campaign, uncertainty tends to collect because each observation is so hard won and so local. The radar map may tell you a lake exists. The altimetry record may show filling and draining. The borehole camera may reveal debris, sediment, or the lower ice interface. The water sample may show cells, chemistry, or dissolved gases. Yet even after all that, large questions can remain. How representative is this point? What is happening beyond the borehole? How much does the lake change over time? Is this basin isolated or networked at the moment that matters? Distance, darkness, and isolation do not merely slow the flow of information. They change the ratio between what we can infer and what we can directly confirm. On the human side, isolation also changes how cautious people must become. BAS's station information makes clear that even station communications can be disrupted, and field manuals for Antarctica repeatedly stress survival training, radio use, weather, and remote field discipline because the environment does not tolerate casual mistakes. In a subglacial lake setting, that same discipline extends down into the science. A risky deployment is not only risky for the instrument, it is risky for the whole campaign because the campaign has so few spare chances. The isolation of the site turns prudence into part of the scientific method. People have to move more slowly, verify more often, and accept that not doing something may sometimes be the responsible choice. That can feel frustrating if you imagine exploration as bold forward motion, but in Antarctic subglacial work, restraint is often what keeps the expedition from becoming a story about what almost happened. Darkness below the ice changes biology in a related way. BAS explains that microbes in isolated subglacial lakes would not gain energy through photosynthesis, but by processing chemicals, especially those concentrated in sediments. NASA's astrobiology reporting on Willans and subglacial lake environments says the same in broader terms. These are cold, dark, low-nutrient systems where life, if present, survives without sunlight. That means darkness is not just an observational inconvenience. It is one of the reasons the ecosystem itself may be sparse, patchy, or heavily tied to very specific chemical niches. In a sunlit lake, biology can often be more broadly distributed because the energy source is above. In a subglacial lake, the interesting biology may be clustered around sediments, chemical gradients, or inflow pathways. Darkness therefore changes both the life that may exist and the odds that a single borehole will reach the most informative part of it. Distance does something similar to time. When a mission spends years preparing for a short access season, every field day becomes unusually loaded. BAS's Ellsworth plans separated long preparation from a brief summer access campaign, and the successful Willans and Mercer efforts also show how short the true science window can be, once the whole exists. So the field team is not only far from help, it is far from another chance. That changes how everyone thinks. Every calibration matters a little more, every sample order matters a little more, Every postponed deployment carries more weight, because the borehole may not remain suitable indefinitely, and the next season is not just next week with a different diary page. Distance stretches consequence across time. The lake is hard to reach in space, and therefore each moment of access becomes hard to waste in time. And then there is the emotional effect, which is not usually written into technical papers, but is there all the same. A remote buried lake under Antarctic ice is difficult not only because of what it is, but because of what it does to the people approaching it. It removes normal confidence. It removes the comforting sense that a place can be looked at from several angles until it starts making sense. It narrows action, narrows sight, narrows access, and then asks for exceptional cleanliness and care on top of all that. In such a place, even success can feel partial. You may have reached the lake and still know that most of it remains unseen. You may have measured water and still know that the wider setting is inferred rather than observed. Isolation changes expectations. It teaches everyone involved that "we were there" can still mean "we barely touched the place." That is really the core of it. Distance means you bring your own world with you. Darkness means you cannot simply look and understand. Isolation means support, comparison, and repetition all become harder. Put those together, and the environment starts controlling not only the method of exploration, but the scale of truth you can claim at the end. You can gather real evidence. You can make careful interpretations. You can even make remarkable discoveries. What you cannot easily do is turn that buried lake into an ordinary field site where movement, visibility, and repeated access gradually dissolve uncertainty. The setting protects itself by staying hard to inhabit, and once the environment itself is shaping every choice in that way, another concern becomes impossible to ignore, because the problem is no longer only whether we can reach these lakes, or even whether we can study them without contaminating them. It becomes whether there may be forms of life down there that have never had to deal with us at all, and whether the very act of finally arriving could disturb something that has remained separate for longer than we can easily imagine. What begins to emerge here is a different kind of fear from the ones that usually belong to exploration. It is not the old fear of getting lost, falling through ice, or watching a machine fail in the dark. Those fears are real enough, but they are familiar. The deeper fear is quieter. It is the fear that the first time we truly touch one of these buried environments, we may change it before we understand it. Not because we are reckless, and not because Antarctic scientists are careless, but because the place below the ice may be biologically sparse, chemically delicate, and isolated enough that even a careful arrival is still an arrival. The Antarctic Treaty System now treats that concern very seriously. Resolution 2 from 2017, which endorses SCAR's Code of Conduct as current best practice, explicitly states that Antarctic subglacial aquatic environments may support exceptional, potentially unique and diverse microbiological communities, and that they may be at risk from research activities through introduced non-native microbes or released contaminants. That is not the language of romantic adventure. It is the language used when people understand that first contact is itself a scientific risk. There is something important in that wording. It does not say these lakes definitely contain dramatic, undiscovered life in the way fiction likes to promise. It says they may support exceptional and potentially unique microbiological communities. That is a smaller claim in one sense and a much bigger one in another. Smaller because the focus is on microbes rather than hidden fish, blind amphibians, or some Antarctic creature with an unfortunate attitude problem. Bigger because microbes are exactly the sort of life that can be both scientifically profound and very easy to disturb. If an ecosystem is based on very low energy, slow growth, chemical gradients, and long isolation, then it does not need a dramatic accident to be altered. It may only need a few extra cells, a trace amount of modern carbon, a change in oxygen, or a piece of equipment carrying DNA from the surface. The US National Academies said this plainly years ago. contamination of subglacial aquatic environments during drilling, sampling and monitoring cannot be eliminated, only minimised. They also recommended that exploration protocols should assume all such environments contain or may support living organisms. That is a careful scientific position, but emotionally it amounts to this. Behave as though something living may be there before you have proved it, because the cost of assuming otherwise may be irreversible. Once you accept that principle, the whole subject changes tone. A buried lake is no longer only a hard place to reach. It becomes a place where caution must arrive before certainty. That can feel backward to people used to exploration stories. Usually we imagine that first we get there, then we look around, then we decide how careful to be. Subglacial lake science does not allow that sequence. The care has to come first, because by the time you have enough evidence to know whether a lake contains a rare or isolated biosphere, you may already have introduced your own biology into it. The National Academy's report went further still, warning that the inadvertent introduction of microbes that might grow in these waters is of highest concern, and noting that exogenous DNA would interfere with research using molecular methods. In other words, contamination threatens not only the environment itself, but the truth of whatever you later claim to have found there. That last point is one reason the fear feels so particular. Scientists are not worried only about harming life in a general environmental sense, though that is part of it. They're also worried about telling a false story. Imagine the most fragile version of discovery. You drill into a lake under the ice, collect water or sediment, and detect cells, DNA, organic molecules, or a metabolic signature. Under ordinary conditions, that would be exciting enough. In a subglacial lake, it would be followed immediately by a colder question. Whose life is it? Is it native to the lake? Did it descend from the borehole water? Did it arrive on a cable, a sensor housing, a gasket, or the skin of an instrument that was cleaned but not quite clean enough? The National Academies stressed that even exogenous nucleic acids matter here, because outside DNA can compromise efforts to identify the true microbial community. So the fear of disturbing life and the fear of mistaking contamination for life are really the same fear seen from two angles. Either way, we become part of the result. What makes this more than a theoretical concern is that subglacial lakes are not sterile in the simple way people once hoped or assumed. The first direct clean access sampling of subglacial Lake Willans revealed metabolically active microorganisms in the water and superficial sediments, with a chemosynthetically driven ecosystem of bacteria and archaea. NASA's astrobiology summary of the work describes methane-eating microbes in the lake, and the original Nature paper reported thousands of bacterial and archaeal types in the sampled material. That matters because the argument is no longer about whether life beneath the Antarctic ice is imaginable. It is about how to study real life that has already been found in at least some of these systems, without overwriting the evidence with our own presence. Mercer Subglacial Lake makes the point even sharper. Work there showed that the sediments and water also contain active microbial communities, and a 2025 Nature Communications study reported that most of the genomes recovered from Mercer samples correspond to new species and taxonomic groups, with phylogenomic and functional evidence supporting genetic isolation from marine and surface biomes. That does not mean every organism in Mercer evolved in perfect, uninterrupted seclusion from the dawn of time. Scientists are more careful than that. But it does mean the community sample there appears highly distinctive, shaped by prolonged subglacial conditions and relative separation from surface gene pools. So when people speak about disturbing life that has never known us, there is now a concrete basis for the phrase. At least in some lakes, the microbial communities are not just alive. They are unusual enough that our arrival can no longer be treated as harmless background noise. The instinctive human response to this is often slightly theatrical. We picture life as something you can frighten, chase, poison, or physically trample. Subglacial life changes the scale of the worry. Microbial ecosystems can be disturbed without anything that looks dramatic from the surface. A few added nutrients may favour some organisms over others. A little oxygen could alter redox-sensitive metabolisms. Stirring the sediments may transfer cells from one habitat into another and erase useful layering. The national academies warned explicitly that research activities targeting one component of a subglacial environment may contaminate or alter another. Sampling can disturb internal stratification and change physical and chemical structure. Sediment sampling can transfer biota from the bottom into overlying waters and ice, compromising later measurements. This is the kind of disturbance that rarely makes headlines because it is not spectacular. Scientifically, though, it may be the most serious kind. That is why the ethical tone around these lakes resembles planetary protection more than ordinary environmental fieldwork. The SCAR Code and the Antarctic Treaty Resolution do not speak as though this is just another ecosystem with access difficulties. They speak as though these places are special precisely because of their combination of isolation, scientific value, and vulnerability to human introduction. The National Academies even recommended that certain exemplar pristine subglacial environments be designated as Antarctic Specially Protected Areas for long-term conservation once enough information exists to describe them properly. There is a revealing seriousness in that recommendation. It suggests that some subglacial environments may deserve protection, not merely while they are studied, but in order to preserve them from too much study done too soon. Part of the fear comes from pace. Surface ecosystems often have some resilience because they are already in contact with weather, dust, migrating organisms, seasonal flux, and all the usual movement of life. A subglacial microbial ecosystem may operate far more slowly. BAS notes that microbes in isolated Antarctic lakes have no access to sunlight and instead rely on processing chemicals, often associated with fine sediments. Their 2021 work also suggests that some isolated lakes may be more habitable than once thought because dynamic circulation can keep fine sediments suspended and distribute resources through the water column. That is scientifically exciting, but it also means the whole lake body may matter biologically, not only the sediments at the bottom. If life is spread through the water column as well as concentrated in certain zones, then contamination at entry or mixing caused by sampling could affect more than one niche. In an energy-limited environment, a small intrusion may persist longer than one would like. And then there is the awkward question of novelty. Scientists are careful not to promise that every subglacial lake contains a wholly unique evolutionary drama. Some are active and connected. Some may exchange water over relatively short timescales. Yet the Mercer genomic study still found broad evidence of novelty and genetic isolation, while BAS has said that life in long isolated lakes could be just as ancient as the settings themselves and could reveal how organisms adapt under persistent extreme cold. Put those together and the emotional logic becomes clear. You do not have to believe in bizarre new branches of life to feel the weight of this. It is enough to know that the microbes below may represent combinations of genes, metabolisms, and survival strategies shaped by conditions almost never found at the surface. Disturbing them would not only be ecological harm, it would be the loss of an unusual evolutionary record. There is a sentence in the National Academy's report that quietly captures the whole difficulty. The existence of these environments on the Antarctic continent makes them part of the common heritage of all humankind. That phrase sounds grand, but here it leads to a very practical burden. If these places belong in some sense to all of us, then no single expedition gets to treat them as disposable opportunities. A failed measurement is one thing. A disturbed pristine environment is another. That is why multinational oversight, environmental review, and codes of conduct are folded into the science from the beginning. It is also why the fear of disturbing life is not just private anxiety among careful researchers, it is built into governance. The rules exist because the worry is real enough to legislate around. What makes the fear especially difficult is that avoiding disturbance completely may be impossible. Again, the National Academies were blunt about this. Contamination can be minimized, not eliminated. That means every mission operates under a kind of moral and scientific asymmetry. Researchers can do almost everything right and still know that some level of introduction is likely. The question then becomes, what level is acceptable, and acceptable to whom? Acceptable for preserving the environment, acceptable for trusting the samples, acceptable for future science, acceptable for an ecosystem that cannot vote, complain, or file a review, but may still be changed by our presence. The report proposed a provisional cleanliness standard based on the number of microbes present in deep glacial ice, essentially trying to keep introduced microbial loads no higher than that natural baseline. It is a sensible approach, but it also has the feel of a line drawn by people who know there is no perfectly clean doorway, only cleaner and dirtier versions of arrival. This is one reason the fear can sound almost philosophical, when in fact it is technical. We're not talking about whether humans should ever touch difficult places. We already do. We're talking about how the act of observation becomes part of the system when the target is small, ancient, and biologically subtle. In subglacial lake work, the observer is unusually hard to subtract out. The borehole changes flow, the hardware adds surfaces, the sampling order can alter later measurements. The drill water, even when filtered and UV treated, still has to be accounted for. The National Academies even warned that robotic devices moving between different levels in the ice and lake bed can transfer cells from one environment to another. So the fear of disturbing life is not a sentimental add-on to the science. It is a way of describing observer effect at the scale of an ecosystem. There is also the question of what counts as harm in such a place. If one imagines environmental harm only as obvious death or visible damage, then subglacial lake caution may seem excessive, but microbial ecosystems are not judged only by whether they remain alive. Their structure matters, their relative abundances matter, their chemistry matters, their genetic signals matter. An introduced microbe that does not take over the lake could still complicate community analysis. A trace contaminant that does not poison anything could still alter the chemistry enough to confuse interpretation. A disturbed sediment surface might recover physically while still losing its original layering. In low biomass, high uncertainty environments, gentle-looking change can be scientifically severe. That is why the fear is less about dramatic destruction and more about irreversible blurring. Once you blur the baseline, you do not get the untouched version back. Willans and Mercer also teach a useful restraint here. They show that careful, clean access work can reveal life without obviously collapsing the entire enterprise into contamination. That is encouraging. It means the fear is not paralyzing. It is productive when handled properly. Scientists can access these systems, retrieve valuable data, recover sediments, and still improve the methods for the next attempt. NSF's 2023 report on Mercer highlighted the first layered sediment sample from beneath the modern Antarctic ice sheet, obtained through a clean access campaign that used a UV collar to irradiate contamination sources at the borehole. That is progress, and it deserves to be treated as such. But progress here does not cancel the fear. It validates it. The reason the progress matters is precisely because the teams worked as though disturbing the environment would be a major failure. Another layer to the worry comes from comparison with icy moons. NASA repeatedly points to Antarctic subglacial lakes as analogues for places like Europa and Enceladus, because they combine darkness, liquid water, pressure, chemical energy, and difficult access. That connection adds a strange seriousness to the ethics of Antarctic drilling. If Earth is where we practice for responsible contact with hidden aquatic ecosystems, then what we learn here becomes a model for how we treat potentially habitable environments elsewhere. A careless approach in Antarctica would not only endanger local science, it would also set a poor example for planetary exploration, where contamination concerns are even more central. Seen that way, the fear of disturbing life that has never known us is not just about one lake beneath the ice. It is practice for how humans behave when entering any sealed biological possibility. There is a quieter emotional truth beneath all of this. Microbial life does not ask for sympathy in the way animals do. It has no face, no movement visible to us, no easy way to trigger the instincts that make people say, "Be careful, something living is there." And yet in some ways, microbes deserve even more caution in a place like this, because they are easy to ignore and easy to overwrite. A lake that has remained dark under Antarctic ice for ages may host communities whose entire existence depends on stable chemistry, sparse energy, and separation from the noisy biology of the surface. They have never known our warmth, our plastics, our fuels, our skin cells, our DNA fragments, our metal surfaces, our haste. The phrase sounds emotional, but the science supports it. Relative isolation from surface gene pools, dependence on unusual energy pathways, and long environmental separation are exactly what the Mercer and Willans' work have begun to document. And because the evidence is still partial, the fear remains unresolved in a useful way. Scientists know enough to be worried and not enough to be relaxed. They know there is life in some subglacial lakes. They know contamination cannot be completely avoided. They know some communities appear metabolically active and, in Mercer's case, genetically distinct from marine and surface biomes. They know that some lakes may have been isolated for immense spans, and that these environments may be scientifically unique. What they do not know, not yet, is how many other lakes host similarly distinctive ecosystems, how fragile those systems are to small intrusions, and how much disturbance can occur before the baseline is lost. That uncertainty is exactly what keeps the caution alive. So the fear is not melodrama. It is discipline wearing an emotional face. It is the recognition that the first visitor to an ancient microbial world should not become its loudest signal. It is the recognition that in some places knowing less for longer may be better than knowing more through contamination. It is the reason treaties talk about stewardship, why codes of conduct assume life may be present before proof is in hand, why clean access systems are so elaborate, and why some scientists would rather delay access than hurry into a lake with the wrong method. In ordinary exploration, boldness is often praised. Here, restraint is the bolder thing, because it asks curiosity to slow down in the presence of something smaller and older than us. And once that restraint is in place, another issue comes into view, because the story does not end with fear. Science has still managed to reach a few of these lakes, to sample water and sediments, and to pull back fragments of a world under the ice. Those findings matter very much, and they show both how much has already been achieved and how narrow that achievement still is. By now it would be easy to leave the whole story in a state of permanent frustration. The lakes are hard to reach, the drilling is difficult, the contamination risk is serious, the machines are always one stubborn component away from embarrassment. The setting itself behaves like a long formal objection to human convenience. And yet, for all of that, science has not come away empty-handed. In fact, what researchers have managed to find so far is already enough to change how Antarctica is understood. The important thing is to be honest about the scale of those findings. We have not opened these lakes up in the way people open a cave system or map a stretch of sea floor. What we have instead are a handful of narrow, carefully won glimpses, and those glimpses have turned out to be far more interesting than a sensible person might have expected from cold, dark water under ice. The first thing scientists have really managed to find is that the hidden lake world under Antarctica is not a curiosity made of one or two isolated examples. It is a continent-scale hydrological system. In 2025, a Nature communication study using a decade of Cryosat-2 radar altimetry identified 85 additional active subglacial lakes, increasing the number of known active Antarctic subglacial lakes from 146 to 231, and bringing the total number of known Antarctic subglacial lakes to 766. That same study documented 37 complete drainage events, 34 complete filling events, and 5 interconnected lake networks, showing that the water beneath the ice is not simply sitting in place like a collection of sealed bottles. In many areas it moves, fills, drains, connects, and changes the surface above in measurable ways. So before we even get to direct sampling, one major result is already secure. Antarctica's underside is hydrologically alive. That matters because it changes the original image people tend to carry around. The hidden lakes are not all giant ancient chambers waiting in perfect silence. Some are stable, some are active, some are part of drainage pathways that alter how the ice sheet behaves. That may sound like background information beside the search for life, but it is not background at all. It tells scientists where to drill, how to interpret a water sample, and whether the lake they reach is likely to be a long isolated system or part of a more rapidly circulating network. In other words, one of the biggest findings so far is that subglacial lake is not one type of environment. It is a family of environments, and the family is more dynamic than earlier generations of polar science could prove directly. The second big finding is simpler and more startling. At least some of these lakes are alive. That sentence still deserves to be handled carefully, because people hear alive and immediately begin designing creatures that sound expensive to animate. What science has actually shown is more modest and in its own way more profound. When the Wizard team cleanly accessed subglacial Lake Willans in January 2013, they recovered water and sufficient sediment samples and identified living cells in the material. Later analysis showed that the lake hosts a diverse assemblage of bacteria and archaea, and that the ecosystem is chemosynthetically driven. In plain terms, the lake does not depend on sunlight. The resident microbes make a living using chemical energy sources available in that dark environment. That is one of the clearest and most important findings yet obtained from a subglacial lake anywhere on Earth. Willans became especially important because it did not just show that cells were present, it began to show how the system works. The Royal Society synthesis on Lake Willans says the microbial community includes organisms related to species known to use reduced nitrogen, sulfur, iron and methane as energy sources, and that the water chemistry is dominated by weathering products from silicate minerals with a minor seawater influence. The 2014 Nature paper described the lake as a diverse and metabolically active community, while later reviews note that chemoautotrophic and methanotrophic activity in the lake was sufficient to support heterotrophic demand. NASA's astrobiology materials put one especially memorable detail into the public record. Methane-eating microbes appear to consume methane moving up from the sediments, helping explain why methane concentrations differ so sharply between deeper sediment and the overlying water. This is not life barely hanging on in a theatrical way. It is a functioning microbial ecosystem with internal energy flows and biogeochemical roles. There is something nicely humbling about that result. Many people instinctively assume that a dark lake under 800 meters of West Antarctic ice would be biologically poor to the point of near emptiness. Lake Willans did not cooperate with that assumption. It showed that active microbial ecosystems can persist in deep, dark subglacial water, and that they can do so through chemistry rather than sunlight. It also suggested that the subglacial environment may influence larger biogeochemical cycles by mobilizing elements from sediments and bedrock and eventually contributing materials downstream toward the ocean. So one of the things scientists have managed to find so far is that the Antarctic ice sheet is not only a frozen mass on top of rock. In some places, it shelters working ecosystems that are tied to the geology beneath them. At the same time, Lake Willans also taught an equally important lesson in limitation. The access was extraordinary, but the actual observational window remained narrow. Wizard sampled through one borehole and worked quickly. That means the findings from Willans are powerful, but they are still findings from a limited point of entry into one active lake. Scientists know life is there. They know the ecosystem is metabolically active. They know something about the chemistry and energy sources involved. What they do not have is the kind of broad, free-moving survey that would let them map the entire ecological variation across the lake basin. So even the first great success in this field came with a reminder attached. We found life, yes, but we found it through a keyhole. Mercer Subglacial Lake pushed the story forward by showing that Willans was not a one-off miracle. SALSA reached Mercer in late December 2018 by drilling through 1,087 metres of ice into a lake with a water column about 15 metres deep. During roughly 10 days of science operations, the team collected 60 litres of lake water, 10 litres of deep borehole water, microbial particulates filtered from about 100 litres of lake water, 10 multi-cores, 2 gravity cores up to 1.76 metres long, CTD profiles, current measurements, and images of the lower ice, the lake interface, and sediments. That list may sound procedural, but in the history of subglacial lake science, it was a major step. It meant researchers were beginning to move from we got in once to we can recover multiple types of evidence from a second lake and compare systems. Mercer also clarified something that had been suspected for a while. Not all subglacial lakes tell the same story. NASA's astrobiology overview notes that Mercer is connected to a broader hydrological system and may have water replaced on the order of a decade, which is very different from the older image of a completely sealed static lake. That already makes Mercer useful as a contrast with more isolated systems such as Vostok. What scientists found there is therefore important not only in its own right, but because it broadens the range of known subglacial environments. We're no longer limited to one cleanly sampled active lake. We now have a second one with a different location, depth, hydrological context, and sample set. That is still a tiny number compared with the hundreds of lakes known beneath Antarctica, but in a field this difficult, 2 cleanly sampled lakes is enough to start seeing pattern instead of anecdote. One of Mercer's most valuable contributions has come from its sediments. In 2023, the National Science Foundation reported that the SALSA team had recovered the first layered sediments from beneath the modern Antarctic ice sheet. The analysis suggested insights into periods when the Antarctic ice sheet was smaller than it is now, and the sample was described as extending interpretable subglacial activity from merely a few decades toward almost 2 centuries. That may not sound dramatic if one is hoping for ancient monsters and glowing bacteria with publicists, but scientifically it is a serious gain. Layered sediments turn a hidden lake into a partial archive of changing ice sheet and environmental conditions rather than a single modern snapshot. One of the things scientists have managed to find so far, then, is that subglacial lakes can preserve a readable history, not just a present-day habitat. The Mercer sediment work became even more interesting in 2023 when ISME Communications published a study on a 2.06 metre composite sediment profile from the lake. That study found that bacterial and archaeal communities in the superficial sediments were more abundant and diverse than those deeper down, and that many of the dominant taxa were related to chemolitho-autotrophs capable of oxidizing reduced nitrogen, sulfur, and iron compounds. It also found that dissolved methane, total organic carbon, and water content were strong predictors of community composition, and that isotopic evidence pointed to legacy marine organic matter as an important carbon source for biosynthesis. That is a very compact set of results with a lot hidden inside it. Mercer is not simply a dark puddle with microbes in it. It appears to be a chemically structured environment whose biology is tied to old marine inputs, sediment conditions, and redox chemistry. That same study also suggested something larger than a single lake. By comparing Mercer sediments with those from Willans and nearby grounding zone settings, the authors argued for evidence of a subglacial meta-community linked through the transport of microbes, water, and sediments beneath the West Antarctic ice sheet. That is a striking idea. Instead of each hidden lake being understood as a completely independent biological island, some may be connected as parts of a broader under-ice ecological and hydrological network. If that interpretation holds up as more samples become available, then one of the biggest findings so far is not just that life exists beneath the ice, but that subglacial life may be regionally connected by the movement of water and materials under the ice sheet. Mercer then went a step further in 2025. A Nature Communications paper using 1,374 single-cell amplified genomes from Mercer water column and sediment samples found that most of the recovered genomes correspond to new species and taxonomic groups, with evidence supporting genetic isolation from marine and surface biomes. The same study identified a diversity of microbes including Pertesibacteria and reconstructed metabolic possibilities suited to a low-energy, dark, isolated environment. That matters for two reasons. First, it shows that subglacial microbiology is no longer limited to counting cells or detecting broad groups. Scientists are now resolving genomic structure at a much finer scale. Second, it means the biological novelty of these lakes is not merely speculative language used to make funding applications sound interesting. At least in Mercer, a substantial part of the sampled microbiome appears to be genetically unusual relative to known surface and marine communities. There is a temptation here to oversell things and start speaking as though Mercer has yielded an entirely separate hidden tree of life. That would be too much. The better way to put it is calmer and more accurate. Scientists have managed to find that the microbial communities in Mercer are diverse, metabolically complex, and in many cases not closely matched to known surface or marine lineages. That is already enough to justify the caution and excitement surrounding these lakes. A world under the ice that contains genetically distinctive microbes adapted to darkness, low energy, and high pressure is interesting without any exaggeration at all. Lake Vostok sits in a different category, and that difference is itself one of the important findings so far. Vostok has given science hints rather than clean certainty. NSF reported in 2003 that two teams found bacteria in accreted ice roughly 120 metres above the lake interface, suggesting that microbial life might thrive in the system. Later reviews of frozen borehole water and accretion ice have continued to argue that some apparently indigenous microbial signatures may be present. At the same time, contamination concerns have never gone away, and even the early NSF summary stressed that drilling had been deliberately stopped to avoid introducing materials into the lake, and that contamination issues remained unresolved. So the finding from Vostok is not, we know what lives there. The finding is that Vostok remains scientifically compelling precisely because it has offered suggestive biological clues without yet permitting the kind of uncontested clean interpretation researchers would want. That ambiguity matters because it keeps the field honest. If Willans and Mercer are the success stories of clean access, Vostok is the reminder that access and certainty are not the same thing. Scientists have managed to find evidence consistent with microbial life in material related to the lake, and they have confirmed that Vostok is a vast buried freshwater body with enormous potential value for climate, geology and biology. What they have not managed to do is turn it into a cleanly understood ecosystem. In a way, that is one of the most truthful findings of all. Some of the most famous subglacial lakes remain more legible as promise than as direct knowledge. There is another practical result from all this work that should not be missed. Scientists have learned that clean access itself is possible, though difficult, and that careful sampling can return trustworthy information about both water columns and sediments. The Antarctic Environments Portal notes that only 2 lakes at the edge of the West Antarctic ice sheet have so far been sampled cleanly for water and sediment. Willans in January 2013 and Mercer in December 2018. That sounds like a very small number, and it is. But in a field where failure can come from logistics, refreezing, contamination, or plain bad luck, 2 successful clean access lakes is also a proof of concept. It shows that we can do this at least in some settings, even if what we get back is still narrow compared with the vastness of the hidden environment. So what have scientists managed to find so far? They have found that Antarctica hides hundreds of subglacial lakes, and that many of them are active parts of a larger drainage system. They have found, through Willans, that at least one subglacial lake hosts a living chemosynthetic microbial ecosystem, using rock and sediment-linked chemistry rather than sunlight. They have found, through Mercer, that a second cleanly accessed lake also contains active microbial communities, that its sediments preserve clues to past marine incursions and ice sheet change, and that its microbiome includes many apparently novel and genetically isolated lineages. They have found, through Vostok and accretion ice studies, that some of the deepest and most famous lakes continue to hint at life, while also warning us how hard clean interpretation really is. And they have found, through radar and satellites, that the hidden hydrology of Antarctica is dynamic on a continental scale. That is already a remarkable list, even though it still feels like notes taken from the hallway outside a locked room. What they have not managed to find is just as important. They have not mapped whole lake basins in detail from inside the water. They have not conducted repeated long-term autonomous exploration inside multiple lakes. They have not produced broad visual surveys of these environments the way oceanographers do on the seafloor. They have not cleanly sampled most of the lakes we know about. And they have not yet turned the deepest, most isolated targets into places we can study with confidence across space and time rather than through one carefully managed hole, which is why the story naturally moves from what has been found to something more difficult and more honest. Why, even after all these impressive discoveries, true exploration still remains just out of reach. After everything we have covered, the strangest part of this story is that the phrase "we have reached these lakes" can sound much bigger than it really is. Scientists have now cleanly sampled only 2 Antarctic subglacial lakes for both water and sediment, Willans in January 2013 and Mercer in December 2018. That is a real achievement, but it is also a very small number beside the hundreds of subglacial lakes now known beneath Antarctica. The same research field that has shown us a hidden continent-wide water system has also shown us how little of that system we can actually enter in a direct, sustained way. So when we ask why we still cannot truly explore subglacial lakes, the answer begins there. We can touch a few of them. We can sample a few of them. We can infer a great deal about many more. What we still cannot do is move through them freely, revisit them easily, and study them across space and time the way true exploration would require. That difference between access and exploration matters more than the wording first suggests. Access means making one narrow opening through the ice and lowering carefully chosen instruments through it before the hole changes too much. Exploration means something larger. It means mapping a place from more than one position. It means following variation from one part of the lake to another. It means being able to return repeatedly, compare conditions over time, deploy long-term instruments with confidence, and say that what you found was not just true at one point directly beneath one borehole for one short interval. The current Antarctic lake missions are extraordinary precisely because they have been able to do a little of that under almost unreasonable conditions. But the record from Willans, Mercer, and the earlier Ellsworth planning all says the same thing in different ways. The operational window is short, the borehole is temporary, and the science has to be tightly prioritised before the work even begins. The geometry of the problem is one reason true exploration still slips away. Nearly everything we know from direct entry has come through a single vertical shaft. Mercer was accessed through a borehole about 0.4 metres wide, through 1,087 metres of ice, maintained for about 10 days. Willans was sampled through one borehole over roughly 3 days of scientific operations. That is not a criticism of those missions. It is exactly why they are so impressive. But a single vertical shaft does not turn a hidden lake into an open field site. It gives you one puncture point. From that point you can profile the water, collect samples, image the lower ice and sediment, and recover cores. What you cannot do, at least not yet, is move laterally through the basin in any rich and sustained way. You cannot casually follow a shoreline because you do not have one. You cannot stroll toward a deeper basin because there is nowhere to stroll. You cannot quickly decide that the interesting chemistry is probably 50 meters to the left and then head over to check. The door is too small, too temporary, and too precious for that kind of freedom. Time is the next part of the answer. and it is just as stubborn as geometry. The borehole begins trying to stop being a borehole almost immediately. The Ellsworth Environmental Evaluation described deploying a thermistor string before the borehole refreezes, which is a very matter-of-fact way of reminding everyone that the access route is temporary by nature. Willans required active management of the upper borehole to keep it usable, and Mercer needed repeated reaming after breakthrough to maintain access during operations. So even when the drilling works, the lake does not become available in the ordinary sense. It becomes briefly available. That changes the entire style of science. Instead of living with the environment long enough to let questions develop naturally, the team must arrive with a sequence already planned, because the access route itself is on a timer. A place that can only be entered for a short interval through one managed hole is a place that can be sampled very carefully, but not yet explored in the deeper sense of the word. There is also a contradiction at the centre of the whole enterprise, and it is one that modern engineering cannot simply wish away. The kind of machine that would let humans truly explore a subglacial lake would need mobility, endurance, reliable navigation, contamination control, sufficient power, robust recovery options, and the ability to work well beyond the immediate area beneath the borehole. Yet the more capable and extensive such a system becomes, the harder it is to sterilize, the harder it is to lower through a narrow borehole, the harder it is to monitor, and the greater the chance that it becomes the main source of contamination or a permanent loss inside the environment. The national academies were very clear that contamination during drilling, sampling, and monitoring cannot be eliminated, only minimized. Their guidance also stressed stepwise approaches, limited numbers of sites, and the cleanest available technology. In practice, that means the field is set up to favour restraint over roaming. The very caution that makes the science trustworthy is also one of the reasons full exploration remains out of reach. That is why the best existing hardware still behaves more like a careful sampling system than an exploring vehicle. The Royal Society review on probe technologies makes the point indirectly by showing how each proposed system has been shaped by its access hole, its drilling method, and the conditions of the overlying ice. These are not broad, free-moving submersibles in the oceanographic sense. They are narrow, specialised, heavily constrained systems designed to pass through a borehole and carry out selected tasks before the window closes. That is an important difference. Ocean exploration became rich when vehicles could move horizontally, linger, return, and work across large areas. Subglacial lake science is not there. It still depends mainly on what can be sent down one hole cleanly and recovered again without losing the route, the sample, or the trustworthiness of the result. The machines are admirable. The environment still decides the scale of their freedom. Another reason true exploration remains impossible is that the lakes themselves are not simple targets. Recent Cryosat-2 work identified 85 additional active lakes, bringing the known active Antarctic total to 231 and the total number of known Antarctic subglacial lakes to 766. The same study documented complete filling and draining events and 5 connected lake networks. That means the environment beneath the ice is not one frozen museum of isolated basins. It includes stable lakes, active lakes, connected networks, and drainage pathways that change through time. In a setting like that, a single borehole is not just spatially limited. It may also be temporally misleading. What you sample at one point may represent one phase in a dynamic hydrological system rather than a stable picture of the whole environment. True exploration would require the ability to track these lakes in repeated and spatially distributed ways, not simply observe one moment at one opening. We're getting better at detecting those dynamics from above with satellites. We're still not able to inhabit them below with the same richness. The clean access successes at Willans and Mercer actually prove this limitation rather than weakening it. Willans showed that a subglacial lake can host a metabolically active chemosynthetic microbial ecosystem. Mercer showed that another lake can yield water samples, sediment cores, imaging, and strong evidence of genetically distinctive microbial life. Those are major discoveries. They tell us the hidden lake world is biologically real, chemically interesting, and scientifically worth the trouble. But they do not add up to free exploration. They add up to 2 carefully managed windows into 2 lakes at the edge of the West Antarctic ice sheet. A window is not a survey. A clean sample is not a map. A few days of access are not a long relationship with the place. In that sense, the greatest triumphs of the field have also defined its limit with unusual honesty. They have shown what can be learned through a narrow opening, and therefore how much remains outside that opening. Ellsworth is part of the answer as well. Even though it is remembered as a failure, the British team did not abandon the mission because the lake was mythical or because the science was unserious. The mission was called off after the team could not properly form the water-filled cavity needed to link the main borehole with the recirculation borehole. That is a useful reminder that subglacial lake exploration is not blocked by one dramatic final barrier. It is blocked by a chain of interdependent operations, any of which can end the attempt. The drill has to work. The water management has to work. The cavities have to link. The hole has to remain usable. The access protocol has to stay clean. The instruments have to perform on schedule. The field camp has to keep functioning in Antarctica while all of this happens. A system this fragile is capable of remarkable success, but not yet of the repeatable, routine access that true exploration would require. There is also a stewardship reason for the limit, and that one may be the most important of all. The reason scientists cannot simply push harder is that pushing harder may be the wrong thing to do. The national academies and the Antarctic Treaty Guidance both frame these environments as unique, vulnerable, and worth protecting for future science as well as present science. The recommendation to proceed stepwise, limit the number of sites, and use the cleanest available technology is not merely a response to technical weakness. It is a deliberate scientific ethic. Some places are so hard to reach and so easy to alter that the responsible pace of knowledge must be slower than our appetite for discovery. A subglacial lake that may contain unusual microbial communities, delicate chemistry, and layered sediments from long isolated conditions cannot be treated like an ordinary destination. The field is not only limited by what it can do, it is limited wisely by what it has decided it ought to do. That creates a slightly frustrating truth. In many areas of science, better technology expands freedom. Here, better technology often expands caution first. A cleaner drill means more confidence in a sample, but not necessarily more room to roam. A better probe means more reliable measurements, but still through one constrained access path. Improved satellite detection tells us far more about where active lakes are and how they behave over time, yet that increase in knowledge from above only makes the limits below more obvious. We can now see that the subglacial hydrological system is broader and more dynamic than once thought. That does not automatically mean we can enter it in a broader and more dynamic way. In fact, the better we understand the complexity of the system, the more cautious the case for deep direct entry becomes. There is a practical funding and logistics side to this too, though it is less romantic than people usually prefer. Truly exploring subglacial lakes would mean repeated multi-season campaigns, more than one access point in some cases, long-lived instrumentation, robust recovery systems, and a level of infrastructure that begins to look less like a delicate science mission and more like a sustained occupation of a protected environment. Antarctica is already one of the most expensive and logistically demanding places on Earth in which to operate, and subglacial lake work sits among the most difficult forms of Antarctic field science. The fact that clean access has been achieved only a few times, and that even a well-funded, heavily planned mission like Ellsworth could still fail at the drilling stage, tells you what the scale problem looks like in practice. We do not yet have a method that is simultaneously clean enough, mobile enough, durable enough, repeatable enough, and affordable enough to turn these lakes into something like routinely explorable places. That is why the phrase truly explore still remains beyond us. To truly explore a subglacial lake, we would need more than a brief clean entry. We would need movement across the lake, not only down into it. We would need repeated returns, not one narrow opportunity. We would need ways to compare locations, follow changes through time, and leave instruments in place or revisit them without turning each attempt into a brand new engineering gamble. We would need those gains without losing the environmental restraint that gives the science meaning. Current practice gives us access, sampling, imaging, profiling, and inference. It does not yet give us habitation, broad mobility, or long-term presence. That is not a failure of curiosity. It is the present boundary between what Antarctica allows and what responsible science can justify. And perhaps that boundary is worth respecting more than resenting. The hidden lakes beneath Antarctica are compelling partly because they have not become ordinary. They are still places where reaching the water is a major event, where a sample is hard won, where a few litres of lake water and a few metres of sediment can change how we think about life under ice, and where the most advanced response to a big unknown is still to proceed carefully and accept small windows of certainty. That can feel unsatisfying if one expects exploration to mean full access, broad maps and confident movement. It feels different if one remembers what the target is, an ancient, dark, cold, often delicate environment that may have spent very long stretches of time without us. In a place like that, not being able to truly explore it yet is not only a technical limitation, it is also evidence that the place has kept some control over the terms of our arrival. So we are left in a very interesting position. We know the lakes are there, we know some are active and connected, we know at least some contain living microbial ecosystems, we know they may preserve records of older ice sheet and environmental conditions. We know clean access is possible in a few cases. We also know that contamination can only be minimised, that the boreholes are temporary, that the access is narrow, that the field windows are brief, and that the hidden hydrology of Antarctica is more complex than one opening can ever capture. Put all of that together, and the final answer becomes quite plain. We still cannot truly explore subglacial lakes because everything required for true exploration, mobility, repetition, duration, confidence, and low disturbance, remains blocked by the same ice, distance, fragility, and restraint that make these places scientifically valuable in the first place. And maybe that is the right note to end on tonight. Beneath Antarctica, the water is still there in the dark, moving in some places, resting in others, holding microbes, sediments, chemistry, and long unanswered questions under a roof of ice thick enough to turn curiosity into a major logistical program. We have learned enough to know that the hidden world below is real, alive in places and much more complicated than the old blank white image of Antarctica ever allowed. We have also learned enough to understand that touching such a world is not the same as knowing it. For now, the lakes still keep most of themselves to themselves, and science, for all its effort and ingenuity, is still only meeting them in brief, careful glimpses.